Good morning.
Good morning. So we start in something like 20 minutes.
Right. I prepared the applause. How do you play the applause? Do I play it directly in the system or I play it on my system?
You know, the only thing I managed to do is to play it on my system, on my speakers, and have the microphone pick it up.
All right, so I give a try.
It's a little bit on the low side.
It's on the low side. Okay.
Yeah.
Maybe I could. Yes. Let me see. The microphone is by the camera. Or what I can do is maybe try to increase them. Unless, of course,
What Jessica was doing, she was playing it in her phone.
In the phone, yes.
And then putting the phone close to the computer.
Yeah, and doesn't even play it anymore. Let me see. Try again.
Perfect.
It's good like that, right?
Yes, it is good. Yeah.
Yeah. I just turned on a bit the sound, so I feel like I'm myself in a room full of applause. All right.
Perfect. I will mute myself now and keep advertising the links and everything.
Good.
And Anna Carla will be your room manager, and so she will be in charge. She's co-host. She will be in charge of.
Hi, Pascal.
Hi, Anna Carla.
Nice to meet you. I'm here in the back.
Okay, all right. Okay. And so she will bring Becky online as soon as she comes, right?
Yes.
Okay. Good morning, Loya.
Good morning, Pascal. How are you doing?
Good. It's a bit early, but that's okay.
It's very early.
7 a.m.
Change. It's a good time for me.
Yeah, for once.
Did you try Shashan's timer that she sent?
Try what? Sorry, no, I've not tried anything.
There was a set of emails about
The timer.
the countdown timer.
Yeah. No, the timer I will do on by myself.
Right. Okay. No worries.
Yeah.
The timer is a little bit complicated. I don't know, because that requires the chair to have his or her video on at all times, which could be a little bit distracting. And I'm not sure the speaker would actually look at it.
Well, this is what I wondered, whether because the presenters, the audience won't see it, but the speaker might see it if they have, depending on how they have their setup, right?
Yeah. In my case,
there was
with
also,
two screens,
I tried it, there was also the issue that when it gets to the end, it just starts again. So I thought a good way to use it is, what I was going to do is, let me show you.
Yeah, you can try for me, because I'm already having like 2 computers and the program and the video here and the apps and the Discord, of course, and the Q&As. And
that's it.
For the timer, this is.
So what I was going to do for Thursday's one, whenever it is that I'm chairing, I was going to put this on and then keep an eye on the time. And when it gets to the end, then move to that.
Yeah.
Because it doesn't sit on the end for very long. And then if you're not careful, it starts counting down again from 15.
Again, and so, yeah.
And the last thing you want is the speaker to suddenly look and notice and think, oh, I still have 10 minutes left.
So for the invited speaker, should I give a 10 minutes sign or only the 5 minutes?
Normally we give 5.
5 only, yeah? I would tell.
Francesco, do you have a view?
I usually I use discretion. So far, what I've seen is that everybody keeps on time, and so I noticed that people on a 30-minute talk already at the 6-minute mark, meaning 25 minutes into the talk, more or less, they already presenting the results, right? And so I don't say anything.
You don't even need to. Yeah, if they are on the last slide, then it's okay.
Yeah.
I wonder if because it's remote, people have actually written themselves a script and they're not rambling as much as we would normally do. You know, when we're on stage and we get nervous and we take longer to speak than we think, because it's unusual for ADASS speakers to keep to time. Yeah,
that's true. That's unusual. And of course, because it's online, they can very well have their own timers and their own clock and everything.
Right.
And yeah.
Yeah, for instance, with Keynote, when I presented, I have my presentation on one screen and the presenter mode on the other screen with the timer.
Mm-hmm.
Which also means, as Kathleen is mentioning in the chat in Discord, that you don't see anything. You don't see faces of people. You don't see anything in Zoom. You know, in my case, this Keynote took over both displays completely.
Okay, because when I did the BOF yesterday, I set up the Keynote so that it wouldn't do that. So it would just be in a window so that I could see the panel.
Yeah.
So I guess
was saying,
depends.
sorry, it depends, yes. It depends on your version of Keynote. Yes, Kathleen is
yeah.
mentioning that in Discord. And that also, that's true. Kathleen had to cut things short at some point yesterday evening, UTC evening. That's true. So what I said is not universally true. Most people keep on time, but not everybody. Of course, it depends on. It depends.
Yeah, that's it. But I think we just have to be prepared to interrupt people, like you know, like people have done, like chairs have done already.
Feel free to interrupt me if I go over time. Please do. Just stop me whenever. Morning all.
Good morning.
Good morning.
I still feel like my voice sounds weird from waking up. Like, you know, when you get up early and you're like, oh, what's wrong with it?
You sound fine to me. You sound normal.
Okay, that's all right then.
So Becky, I will be the chairman this morning.
Great.
Pascal Ballester, I will introduce you as a research fellow at the University of Oxford.
Yep.
And mention that your research field is active galaxy nuclei.
Yeah, sure, that would be great. That's perfect.
All right. Okay.
I don't know if I'm quite bright enough, but my light keeps flickering, so I might have to change its batteries, but who knows where the batteries are? Oh, well, I'll leave it for now.
So Pascal, it's not clear to me what it is you would like me to do as your backup chair.
Well, so normally the backup chair, you jump in when my network connection fails.
When your network
and
dies,
I don't want to share the meeting anymore.
Okay. That was my assumption that this is what you wanted me to do. Otherwise, I'm just going to sit quietly in the background.
Or if I obviously, I don't know, forgot to do something, or then you will just jump in.
Okay, no worries. I'm here, and
Yes.
you know, you can always send me a message if you
right. Yeah, messaging.
You know.
So yeah, with the network, I'm through cable connection here. Should be fine. But yesterday, Kai had really trouble, eh?
Yeah,
The
Kai.
high technology site of Heidelberg. I mean,
So I was talking to Kai, and this is something that might be of interest for all future speakers and future and current chairs and room managers. Apparently, what tripped the whole thing was him sharing his desktop. Because what was happening was that he was already streaming all his presentation and video and everything as his video source. And so when he started sharing the desktop, everything froze. And we have another speaker, I think from HITS, when is her talk? Maybe on Wednesday, I believe. Yeah, Fenia, that will be oral contribution 0198, interactive exploration framework for big data sets. She will be using a similar setup, and so we need to be aware that she might not want to share the desktop. But yeah, Zoom is not handling this, you know, fancy video setups gracefully, as we have seen.
Am I able to test whether my slide, because I've got my two screens, am I able to test if my slides come up all right with the share, or would that break the live stream? Okay.
I will anyway turn off my video, of course, during the
Sure.
talk and so on.
Yeah,
And
So,
mute
Becky,
and only come in if I need to speak then.
we are starting in 5 minutes, so you might want to try your slides.
Yeah,
just
that's what I was
quickly.
thinking. All right, let's. Oh, I can't share screen while the other participant is sharing. Okay. Keynote, share. And if I press play, what do you see?
You see your
screen.
slide full screen in play mode, so it's perfect.
Great. So no presenter notes, nothing like that.
No,
Nothing.
Great, because I can see the presenter notes. So that's what I wanted.
that's what you want.
I always panic that it's not going to work somehow. I lose my mouse though.
Hi Becky, I'm Anna. I'm the
Hi,
film
Anna.
manager today. Hi, nice to meet you. When you are giving the speech, you are going to be highlighted your video, so everyone is going to see you all the time, as well as the presentation. Just to you be aware. Okay.
Yeah, sure. It's why I did my hair when I woke up.
And so basically at the very beginning, you highlight me, I introduce the session and the first speaker.
Yes, well, usually, yeah, I'm going to be highlighting everyone talking, but usually if you talk, the video the highlight will change to your video.
All right.
So it's better if you stay mute when you are not gonna talk like something meaningful.
Yeah.
But I'm going to be like looking at that everyone is in the video when it's supposed to be. Okay. So no problem. Okay.
And
how does the questions work? That'll just be fielded from chat, right?
So the questions will be filled in the Q&A chat, and there might be many. So I will go through and read them verbally, because actually you cannot see them.
Yeah.
Yeah. So I will go through and take the first ones and then stop when the time is ready. And I assume you will keep on time, but otherwise I will give you a 5-minute warning.
Yeah.
For the end of the presentation.
Sure. Just come in with a foghorn at any point. Yeah. You want me to shut up.
What happened now? Okay. What happened to my mouse? The cordless mouse stopped, but I have a cable mouse. Okay.
So we are starting in just a couple of minutes. Also be aware that there might be questions in Discord.
Yes, so,
be aware of
so
that.
they will be in the talk channel.
Yes.
Yeah. Okay. So then I will check a little bit the questions in the 2 channels, but I don't know exactly with the timing, right? Which one is first and so, but I will look depending on the question.
Would it be helpful, Pascal, if I watched the
questions,
the Discord questions and put them onto
the
Q&A screen?
Yeah. Okay. Yeah.
Up to you.
Yeah. No. Please. Yeah. Yeah. Then I follow only one channel.
Yeah. Okay. I'll do that.
Easier. Thanks. Yeah. And I'm going to try my applause again. So, okay. All right. Does it sound okay, the applause? Because the other one, it sounds great. And on the other ones, they were like Noya was telling yesterday, the sound quality was medium, let's say.
It's better than everybody clapping when their mics are not muted, let's put it that way. That sounds horrific when that happens.
So, the mouse is decided to die right now, but I will recharge it. Could you, Noria, just put a test question into the Q&A? And
sure, I'll do that now.
Yeah. And I will close it and just do. All right. Yeah, and we see you, and this has been answered live. And then, okay, so then Becky's answered, and this is done now. All right.
Pascal, I can't write questions in the Q&A.
And you cannot copy and paste.
I can't write questions there at all. I'm on the panel.
And that's true. You're on the. That's right. But how did?
That's okay. I will find somebody here who
Katrina
can do that
okay.
for us.
Yeah, Katrina.
Leave it with me, Pascal.
Yeah. Okay. Hi, Katrina. Good.
So just tell me when, Pascal.
Yes. Are we starting? So we have already 56 participants. So good morning, everybody. We're starting this session this morning this morning in Europe on citizen science. And I'm Pascal Ballester, will be the chairman of the morning session. I'm working by ISO. And our first speaker is going to be Becky Smethurst. Becky is a research fellow at the University of Oxford. And her research field is active galaxy nuclei. She's going to talk on Galaxy Zoo and the Zooniverse. So Becky, I give you the floor and I'll give you a 5-minute time.
Great, thank you. Thank you so much to the organizers for inviting me to talk to you today about how we can use citizen science to classify our data, both in this age of big data that we find ourselves in now, and also moving forward into the next decade. How can we combine citizen science with machine learning as the new generation of telescopes and surveys come online? Because the biggest data sets we've had to deal with so far is the Sloan Digital Sky Survey. Some 4 million spectra taken, right? 2 million galaxies identified, 500,000 quasars, 800,000 stars. I think that classifies as big data in anyone's book. And SDSS have done a fantastic job at making that data public. The question that everyone had from Galaxy Zoo is, how do we classify that data so that it's actually useful to do some science? And one of the hardest things to classify is the shape. It's not something that can be accurately parameterized with a single number. You know, people have tried with things like concentration and asymmetry, but there's just so much variation in both, you know, the shape across the population, but also, you know, in the noise across images, depth of image, everything like that. And so it's very, very difficult to do, at least for a parameterized version of morphology, but also for a machine to do as well. So that's why back in 2007, Galaxy Zoo was launched. It was a citizen science project and a website online that got volunteers to classify the shape of a galaxy so that morphological studies of large populations of galaxies could be done. So this was Galaxy Zoo 1, essentially started with all sort of 1 million Sloan images, and it was a simple elliptical or spiral question. See, there's a couple of sort of things in there about anti-clockwise spirals and clockwise spirals and everything like that. It was a fun result. Someone can ask me about it if they're interested later. And one of the things I love about this image is just how old school internet this looks. I feel like I'm back in like high school all over again when I see this. You're happy to know that Galaxy Zoo looks a bit more like this now, a lot more slick, a lot more modern internet like we're used to. We're on something like the 5th iteration of Galaxy Zoo now, and you can see we're asking much more detailed questions about spiral arm windings, the number of spiral arms a galaxy has. And I like to say, you know, this is a task that even a 5-year-old, if they're keen, could do, right? So it's something that's nice and simple for humans. And Galaxy Zoo spawned off, you know, hundreds, if not thousands now, of other projects that come under the banner of the Zooniverse, you know, everything from classifying penguins in Antarctica to transcribing World War II diaries. You know, there's lots of different projects going on from researchers that all need help classifying data. And that's because of the success of Galaxy Zoo. So back when it first launched in 2007, you know, the astronomers who were on board didn't really have an idea of how popular it would be. There was actually a server meltdown after 3 hours of the launch. And I think that was because the PI went on to BBC Radio 4. Be careful with it. It's a dangerous beast and should be used carefully, because it turns out the Radio 4 audience are very keen to get involved with something like this when you tell them, hi, we need your help to classify galaxies for science. And in the end, the actual whole project was completed in 6 months with over 300,000 people classifying each of the 1 million Sloan images over 40 times each. As I said, still going though, because obviously we've got lots of different surveys. The current one that's just finished, I think we're sort of very close to finishing decals now as well, which is very, very exciting. What it gives you, Galaxy Zoo, though, is a vote fraction, essentially, for the percentage of people who said that a specific galaxy was a disk or a bar or a merger or something like that. So essentially, it gives us a very nice database that we can use to pull out what we're interested in, right? So here I'm showing the percentage of people who said each of these galaxies was a disk, which are these 10 examples. You can see it goes from the least disky up in the top left there to the most disky in the bottom right, that 99% of people agreed was a disk. And you can see it's a beautiful spiral galaxy. And so what that's led to now, as of last week, it's led to a lot of science, right? There's 432 papers on ADASS that mention Galaxy Zoo in the abstract, and 1,550 that mention it somewhere in the text, which I think is an incredible number. It just reflects, you know, the impact of having this database so publicly available to people as well. And so this is the crucial thing here, right? It's the science part of citizen science. Sure, great project, gets people involved, 300,000 people, you know, over 1 million on the Zooniverse as a whole, looks good for your impact, the ref and all that sort of things. But at the end of the day, it's the scientific studies are what are important. So before we get to the sort of combining citizen science and machine learning, I just want to highlight a few results that were actually made possible due to Galaxy Zoo. So the first one of those, and I think the biggest that's probably most well known, is some of the earlier work that was done by Karen Masters and Kevin Shavinsky, showing that blue ellipticals and red spirals, which I'm showing on that bottom row there, weren't actually as rare as originally thought by sort of the astronomers throughout the 20th century. So in fact, red spirals make up 30% of the spiral galaxy population, and blue ellipticals roughly 10% of the elliptical population. And so that's not exactly what I would class as rare anymore in terms of what we can find in Galaxy Zoo. And I think this really was down to the power of citizen science, being able to classify, first of all, a large amount of galaxies so that you could get this kind of statistic, sure. But also the fact that the public had no preconceived notions of color equals shape. The fact that something that looks red would more likely be classed as an elliptical for them. They had no preconceived notions of that. They were completely unbiased, which really was sort of the strength of the crowd here, I think. And I think it's still worth noting that, despite these results, they're over a decade old now, there are still some papers which, very sort of simply cut their sample based on color and say that this is a morphological split. And it's like, no, it's not. And, we've got all these data tables open. So if you're doing something like this, I really strongly encourage you to grab the Galaxy Zoo tables to make sure that if you're trying to split on morphology, you can do it with some accuracy. This also feeds into much more recent work back in 2019 that was led by Karen Masters that we did together with the team. And with this, we wanted to highlight the issues with the famous Hubble tuning fork that I'm showing in the right there. This is sort of the bread and butter for classifying galaxies, right? And it's how we've done it for a long time. And you'll see on both the spiral tracks where Hubble decided there was different classifications, we move from an A classification, an SA, to an SC. And as we move from SA, we go from very tightly wound spiral arms with a very large bulge, all the way to SC, which is much more loosely wound spiral arms with a very small bulge. But actually, when you look in Galaxy Zoo, as you can see in that sort of table of galaxies I'm showing down below, you find all different combinations of tightly wound with a small or a large bulge, or loosely wound arms with a small or a large bulge. And the thing was, I think people had assumed that they were quite rare. The things with tightly wound arms but very small bulges, and the things with loosely wound arms and dominant bulges. I think people thought they'd be very rare if we looked at them. But that wasn't the case when we actually looked again at the classifications. So I'm showing here on the x-axis, this is how large the bulge is. It's sort of a weighted average from the vote fractions we get. And then on the y-axis, it's how tightly wound the spiral arms are. And if you, the tuning fork was sort of the be-all and end-all, what you would expect is this diagonal correlation here from SCs in the bottom corner with very small bulges loosely wound, all the way up to SAs in the top right. But as you can see, that's not what we see at all. And it sort of really changed our idea of how we might classify galaxies, and sort of we're never going to get rid of the Hubble tuning fork probably, but it really did make us rethink how that actually happens, because we can see that the majority of galaxies actually have fairly small bulges and tightly wound arms, and don't fall into those discrete categories that were outlined by Hubble either, right? This is a very continuous sequence. And so that's another thing that I think Galaxy Zoo really helped to highlight. The tuning fork is discrete, right, in its classification of galaxies, meaning there is some threshold that we can draw to say this is the split between spiral things and elliptical things. And this is one of the obviously the big questions in galaxy evolution is how do you evolve from one to the other? And so this is why this split is very, very important. But firstly, when we observe galaxies, we have all of the inherent observational biases that blur that line, first of all. But then also the classifications we make, whether they're analytical, like concentration or asymmetry, or whether they're, say, bulge to total mass ratio in a galaxy as well, or even the vote fractions from Galaxy Zoo, they're all continuous and not discrete. And so I think there's a lot of error that comes when people try and map those continuous classification systems to a discrete system that we're familiar with in terms of Hubble. And so when you have vote fractions like this, the question is, from Galaxy Zoo, I should say, where do you put that threshold then? So that's just a very arbitrary sort of histogram of the, vote fraction of being a disk. Do you put your threshold at 50% of people said it was a disk, 70% of people said it was a disk? And so that was a big discussion early on in Galaxy Zoo, how are people going to use these vote fractions that we gave them? And we suggested, okay, if you want a very, very clean sample, then you should say everything that everybody agrees, at least 70% agreement is a spiral galaxy, is a disk galaxy. And similarly for ellipticals, everything that everybody agrees is 70% agreement, then that's an elliptical. But the thing is, by doing that, you lose so many galaxies in this uncertain region in the middle that is sort of shaded with yellow there. And I don't know about you, but I'm not really partial to throwing out data. I really like to hold on as much as my sample as I can. And so when I came to do my PhD and came into the Galaxy Zoo team, I was very keen to use these vote fractions in a different way. And so in my way, I like to use this example from 2016. I've sort of veered away from using thresholds, and instead I use the classifications provided by the citizen scientists on Galaxy Zoo as weights. So this was a study of mine that inferred the quenching histories of galaxies using photometry, SMESTSS, and GALAX. And it showed that rapid recent quenching was happening in AGN hosts, but not in inactive galaxies. So every single galaxy in my sample is in that blue curve there. It's just that they're weighted by the smooth vote fraction from galaxy, the percentage of people that thought that galaxy was an elliptical galaxy. And every single galaxy is also in my sample is also in that white curve, showing the same thing, except it's weighted by the percentage of people that thought the galaxy was a disk. And so I think the strength of this work really came from, not using a threshold and instead treating the vote fractions as weights, which meant that, as Anthony is so beautifully showing there, no data was thrown away, which I reckon is something to celebrate. Always, always, always. The problem comes with if you don't want to throw data away, what do you do when your data sets are even bigger? And so this is what sort of scares me and keeps me up at night, is the fact that LSST is coming. And it's supposed to be, the idea is identifying 1 billion galaxies. That would mean we're scaling up sort of the original first iteration of Galaxy Zoo 1,000 times. It's just not scalable. Hell, even Euclid is coming in with 50 million galaxies soon, and that's not scalable for what we've been doing either. For this, we're going to have to bring in the machine learning big guns, which have really obviously improved since 2007 at this task of classifying the shapes of galaxies. And the rudimentary way to do this is to use human classified data to produce a training set for a machine. So you citizen scientists classify, you label, you use that to train the machine, maybe to classify LSST images or Euclid images or whatever. But even if you have a 99.9% accurate machine on 1 billion galaxies, that still leaves 1 million inaccurately classified. So the machine is always going to need help. And I think that's really nicely illustrated here. This is actually supernova data, so a little bit of a turn off from galaxies here. This is actually one of the Zooniverse's supernova hunting projects led by Darrell Wright using Pan-STARRS data. And essentially in this project, people were asked to flag if something had changed in a new image compared to a library image, like I'm showing on the left there. And therefore, if they're flagging it, they're saying, yeah, it's worth investigating, it's worth some follow-up. And so a machine was essentially also trained to do the same thing. And so in the graph on the right there, I'm showing the human score on the y-axis. So, what percentage of people basically said that it was worth following up, and then a similar thing from a machine, which was trained to do the same thing. So we're comparing, how likely is it something has changed in a given image? What does a human say? What does a machine say? And after those classifications have been made, an expert has then gone through all of those and flagged them as good or a possible follow-up. They flag them as if they're an asteroid instead, which often crop up on supernova images when you're trying to search them, or possibly even garbage, like cosmic rays, etc., like that in the green points that you can see there. And so this was done for a small sample. And so the idea is that you look at the classifications in this small sample and decide if there's some threshold in score above which you would follow up on observations, so that you could then scale that to a much larger scale when you get more data later. So essentially you want to look for the line that you can draw that selects the most red and yellow things and the least green things. And I hope what you can see is that that's not a horizontal or a vertical line. i.e., so if it was a horizontal line, you would just be ignoring the machine score and you'd only be looking at the human score. If it was a vertical line, you'd be ignoring the humans and only looking at a machine score. I hope you can see that to get the most red things and the least green things, i.e. the most things that you should follow up on and the green things that you should probably just ignore, it's a diagonal line, right? It's a combination of the two. It's machines and humans working together. And that's the key thing that I want to take forward now into the rest of this talk. Machines and humans working together. So how can we apply that to our problem of galaxy classification? Well, let's actually sort of look at some of the images we're actually trying to classify here. I think these are from decals, if I remember right. There's just so many surveys these days, I can't keep on top of it. Now, about a third of these galaxies that you can see here, I hate to say it, but they are boring. I mean, they are. From a machine learning point of view anyway, maybe not an astrophysics point of view. I know there's probably some people out there that elliptical galaxies are their babies and they're very, very protective over them. But from a machine learning point of view, they're very boring. We would expect any model to learn to recognize the sort of, very smooth, fuzzy blobs after fairly few examples. Whereas in the early days of Galaxy Zoo, we were showing hundreds of thousands of these kind of fuzzy blob images to, millions of volunteers. Each of them were classified 40 odd times. You don't need to classify them 40 odd times by the time that, 5 people have told you 100% that's just a fuzzy blob. It's just not efficient. And it's not fair on our volunteers either. And the same thing is true if you've got a machine. It's much more efficient if it can classify them very, very quickly. So ideally, we would only show the volunteers, our citizen scientists, the images that the model most needs help with. So the model should be able to ask, hey, I'm really uncertain about these galaxies. Can you label them for me, please, so I can learn more about them? Humans would then label them. The model would retrain itself with only those most informative galaxies. This is what we call active machine learning that is happening in real time as people classify galaxies. And it's really best used when classifying is very expensive. So a fixed number of volunteers, a very large number of galaxies. And obviously the catch is, how do we know which images the model is uncertain about? So deep learning only gives you a scalar prediction for each of the classification you make. So what we really want to know is the uncertainty around that prediction. And so these slides I've lifted straight from Mike Wormsley. I'm going to put my hands up and say that he is heading up the work in the Galaxy Zoo team. He's a senior PhD student at Oxford. Pretty sure he's on the job market this year as well. So if you want to know more detail about this, then please speak to him because he's probably the best person. For those at least that everything on my slide now means something too. Now, for those who have no idea what in the universe this slide is actually saying, the gist here is that we use a convolutional neural network. And what that's able to do is actually make an estimate for how uncertain it is of its classification or label of a galaxy. i.e. the machine itself can decide probabilistically what it needs the most help with. And so here's what sort of those galaxies look like. The ones that on the left-hand side are the ones that the machine needs the most help with, and the ones on the right-hand side are the ones that, if the machine has decided, it will get very little insight if it shows one of those images on the right there to a human to classify. It's already very certain of its classification, and getting confirmation from a human of the fact that that's just a fuzzy blob, would not be helpful. It's already a certainty to the machine. Whereas those most featured galaxies on the left-hand side there are the galaxies that the machine learns the most from getting a human to classify for it, which is, unsurprising if you think about it. It's probably some feature that's ever so slightly different from a feature that it's seen before. And so I like to think of this as the most and least informative galaxies. How much better do we constrain the model having the humans label that particular galaxy? How informative is it for the machine to learn from that galaxy if it were labeled? And I think it's the machine deciding itself what needs to be shown to a human is what makes Mike's work really, really cool in my book. This is actually live on Galaxy Zoo now as well. So by choosing the enhanced classification arc rather than the classic, which just lets you see a random galaxy from the sample as usual. And we've made sure to be very open with our citizen scientists, with our volunteers, about what we're asking them to do. So, first, that's why we give them a choice, first of all, because some people prefer just a random sample. But we explain that the enhanced workflow, is more efficient, although they're not necessarily seeing every single galaxy in the sample, because I think that's what's quite attractive about citizen science and big data is that you could discover anything. But they're really seeing the ones that the machine needs the most help with, and that will make us more efficient and get more science done. And so, honestly, those tend to be the most interesting galaxies to look at anyway. And so it makes the task more fun. And we find that about 90% of our users actually choose this option as well. And I believe Mike is also currently working on how this sort of active learning can be applied to the classification of fast radio bursts and all that kind of stuff as well. So it's very exciting stuff. So I hope with this, I've managed to convince you that the fact that LSST is coming isn't so dark and terrible after all. We've been able to bring machines and humans together to classify data efficiently on these smaller data sets. And so because we've rolled out these tools on these smaller data sets, I say small in today's standards anyway, as I said at the beginning, they're probably classed as big data to anybody. But because they've been rolled out on the small data sets, it means that when the time comes, we can tackle whatever size data set is thrown at us, in the coming era of really, really big data. And hopefully it'll feel like peanuts to us. Thank you very, very much for listening.
Thank you very much, Becky, for this very nice talk. I think I will play you a big applause
Thank you.
from the big crowd of participants. And we have received a number of questions. There are 2 questions and 1 comment. So the first question from Haro Verkuter is on your slide with the red dots and the purple dots. The question is, it looks like the machine learning is better in classifying than the humans. There is less horizontal spread in the red points. So could you comment on this?
Yeah, sure. It does indeed look like the machine is sort of at first glance, because you have that sort of, I don't know if anyone can see my mouse. I probably can't. You have that sort of concentration of red points in the top right corner, right? And so if you made a split at, say, a machine score of 80%, you would get most of those in. The problem is that you'd also get all of the green things that have a very low human score as well. So I think the key thing there is that the red points are in the top right corner, right? They're not just on the right-hand side. And so that's why if you have the vertical line there, you're still going to get so much garbage that's been labeled by an expert as garbage in your sample that you want to follow up on. And that's why the diagonal line is the thing that, okay, maybe that diagonal line needs to be shifted up slightly. I think that was just for demonstration, for visualization. But that's why with the diagonal line, you would get the highest proportion of the red points that are good, that you want to follow up on, and the least proportion of garbage things, because that's the thing you want to try and get rid of. You don't want to follow up on things that don't turn out to be supernova, because that's expensive in terms of follow-up time.
Okay, thank you. One more question is, how do you know that in the universe that you're only showing galaxies and not other objects, nebulae or blob-shaped other objects?
Yeah, so that comes from the survey pipelines. Usually, for example, SDSS do a very, very good job of classifying through the pipeline whether it is a galaxy or a star, usually from the spectra alone. Doesn't necessarily classify, obviously, the shape of the galaxy, which is what we're interested in. It just classifies not a star, not a nebula, not a quasar, galaxy. And so that comes from the SDS pipeline.
And one more question from Alex Mesheryakov. How many galaxies will need to be labeled in order to annotate 1 billion, so 1A9 LSST objects?
Yeah, good question. So that's sort of one of the things that we've been trying to answer with this. I know that there was these Kaggle competitions that gets people to do some, sort of software writing in order to try and crack one of these competitions where they're given an aim, and that was done with the Sloan Galaxy Zoo. And I remember with the huge data set that they had, the winning entry to the Kaggle competition, actually what they did was quadruple the data set by realizing that the classification is rotationally invariant. So if you have an image of a galaxy, you can rotate it, keep going 90 degrees until you have sort of like the four sort of main rotations of it, and the classification doesn't change. And so the guy who won it actually managed to do that and quadruple his data set, and that made him much more accurate in terms of classifying compared to the humans as anyone else did. And so that meant he needed like 4 million to be accurate on a sample of a million, which is kind of ridiculous. But I think that's getting better. I think with this active learning in the background, starting the machine off being trained on a sample that's much smaller, perhaps sort of the first 50,000 or so, will at least get you the efficiency boost that you need to classify the easy things. And then it's the classifying the hard things that I think will take a lot longer. But you won't need to classify as many as if you'd done the traditional get a human to classify 1 million things and then train a machine. And I think that's another strength of the active learning.
I think we might have, okay, Becky, you're online right now? Mm-hmm. Okay, at least there was some interruption. Oh. I don't know if anybody else, got the answer to the last question.
Yes.
I can say it again if not.
Okay. I have,
yes.
Okay. Was fine, yeah, okay. Good. We have a follow-up to our Verkuter question. Mm-hmm. And in the plot between human score and machine score, mm-hmm. There were in this plot here displayed, there were no samples having a machine score less than 0.5.
Yes.
What does it mean? And is there no instance where the machine is completely wrong?
Yeah, sorry, I should have mentioned that. That was just an initial cut that I think Daryl had done on the machine score to sort of throw out anything that was less than that already. I'm not sure why. Again, this plot is stolen from Daryl, so I guess I could go ask him. But I think it was just an initial cut on the machine score that he'd already done, possibly because he knows the machine quite well and knows that anything that's below that point is probably not worth investigating. So it'll all be in that paper that's linked to the top. So if you're extra interested, I'd check that out. It's a good paper.
Pascal, you're muted.
Okay, I'm mute. Okay, we have one person having the hands up, and that's Jorge. And I will ask him to unmute. Yeah. And to ask the question then. And after that, I will take one more question from Andreas Wichenek, a comment from Peter, and we will stop with a question. Jorge, could you unmute and ask your question? Okay, I don't see Jorge online, but maybe while he's coming, I will bring the question from Andreas Wichenek. Mm-hmm. If you would overplot the galaxies the machine thinks it needs help with, how would the plot look like?
I'm sorry, I'm not sure what plot I'm making there. Could you say that again?
If you would overplot, so probably on the red and the purple plot, if you would overplot the galaxies the machine thinks it needs help with, so the galaxies that are not so classified by the machine, how would the plot look like?
Yeah, so you can't make an analogous plot because you obviously don't get like a similar score in that respect. I imagine that what you would find is that the machine score is very uncertain. So if we go back to Mike's slide, you can see these sort of like little posterior functions that he's got here is various different sort of iterations of the machine. It's very uncertain in the fact that it's very broad. So if you think about that as the machine score that we had before, but obviously there's not an equivalent human score. you would maybe ask sort of 3 or 4 people, and then all of a sudden that would make the machine score very, very certain, and it would perhaps jump this way as you jump to the right. Sort of, I just realized no one can see my mouse, sorry. It would jump to the right as you got more certain of your classification, or you would jump somewhere, I guess. And so there's not an analogous plot that can be made, but you can imagine it, I guess, as going from, you know, somewhere in the middle, moving around because the machine is very uncertain, and then a human score making the machine much more certain in its answer. So.
Good. Then we have a comment from Peter Skoda, mentioning that the principle of active learning is cross-entropy ordered, and have also applied this. This is in the talk comments, so anybody can see it, and they have applied it to finding emission spectra in LAMOST. So
nice.
Okay. And then there was also a hand raised by Jorge Garcia. If you would like to ask a question, please raise your hand again. Otherwise, we will conclude this talk. And thank you very much again. So for the talk, and we will resume in now about 9 minutes for the next presentation. Thank you, Becky.
Thanks.
Okay, Matteo, you're going to give the presentation. Would you want to try sharing your screen?
Sure.
Okay.
I need to, okay. Mhm.
Like a high-flying presentation. Looks good.
Yeah, it's use a double monitor. In one I have a timer, and in the other I have the presentation.
Okay.
And if I launch the presentation, I can't click on Zoom, so I need to first show my desktop, which is well, and okay. I don't know if Becky is still online, but it was really, really a nice talk, and I really, really enjoyed it.
Okay, so we resume the session on citizen science, and I hope you all had a nice coffee and move your legs and so. And now we start with the first talk by Matteo Bacchetti. Matteo is a researcher at Observatory of Cagliari, and he's going to give a talk on Cyclops, the citizen computing pulsar searches.
Thanks a lot, Francesco, and thanks to the organizers for accepting my talk. So what I'm going to tell you today is something about Cyclops, which is a game designed for pulsar searches. So for those of you who don't know pulsars, pulsars are extremely dense objects. They are stars about 20 kilometers wide and with the mass of a 1.5 suns that spin often very fast, up to like 700 more times per second. And in spinning, they illuminate the sky with their beams, some sort of lighthouse. So what we see actually is a pulsed signal. There are many kinds of pulsars.
Matteo, you will need to share your slides.
What?
You will need to share your slides.
Oh, wow. Let me, I'm sharing the slides in theory. So let me.
Maybe you can try to share your screen.
Okay, I'll do it again. You see that now?
We see Jimi Hendrix.
Okay, good. Jimi Hendrix is good. So I was talking about pulsars, these super dense stars with beams that illuminate the sky like a lighthouse. And this is a merger of research on pulsars and on so-called GWAPs, games with a purpose. So these are games designed to let the citizens do science in a different way than citizen science and citizen computing, where you involve people directly, for example, in the beautiful classification work that Galaxy Zoo was doing, or just use their resources like Boeing. A GWAP, a game with a purpose, transforms the physical objects or the chemical interactions into game objects that people interact with, sometimes even not knowing that they're interacting with molecules or proteins, like in the case of Foldit. Let me give you an example of what are the difficulties in pulsar searches usually. First of all, the radio signal travels through the interstellar medium, and it arrives at different times at different frequencies. So if you don't correct for this, you will not see most pulsars, because their signal will be washed out. Also, pulsars are usually, the pulsars we find now are pretty weak compared to the background radio noise, both instrumental and celestial radio noise. So we need to find them by using Fourier analysis. It's the typical way to find periodicities. We do a power density spectrum, we find peaks, we sift through them, eliminating harmonics and broadband noise and all this kind of stuff. And we use an accelerated version of the Fourier analysis, so for frequencies that are changing over time, to find pulsars that are changing their frequencies, either because they're spinning up or because they are in an orbit, so the Doppler effect is changing their frequency. Once we find a promising candidate, we run an epoch folding, which is cutting the light curve. You see the light curve here cut in many pieces, right? And stacked and summed in phase. And if we get the right period, then the signal sums with signal linearly, and the noise sums with noise. So we gain in signal to noise ratio. There is a way to make this process extremely fast and even use it in place of the Fourier transform, which is called fast folding algorithm. It's an old algorithm, like 1969, that basically combines the steps of the folding in pairs of sums, so that we can get many different foldings by shifting the second block we are summing by a certain amount. Cyclops starts from here. So Cyclops is a game that uses modern technologies. It's based on the real-time development platform Unity for the building of the game. Most of the libraries are written in C# because that's what Unity uses, and most of the demonstration libraries we built to develop the algorithms and the server are written in Python. Starting from the fast folding algorithm, we can notice a couple of things. The most important thing, I think, is that there are intermediate steps to the fast folding algorithm. And these intermediate steps contain some already aligned signal, okay? So we can use this method by, instead of running the whole fast folding algorithm together, we can stop at intermediate steps and have similar objects coming out of it. Now, in the first case, a single burst, you can have a fast radio burst, other interesting objects, other interesting signals that are practically indistinguishable from single pulsars. A single burst will happen before combining anything. So you will just take this chunk of data and you will be able to measure a single burst. In the intermediate steps, you will notice that we can find transient pulsations. For example, pulsations that are only happening in the first half of the observation or in some part of the observation. And at the end, we'll be more sensitive instead to persistent pulsations, the ones that last for the whole observation. All of them will have the same approximate shape, because many pulsars have these peaks. They can have a sinusoidal shape, they can have many different shapes, but for the sake of simplicity now, I will say that all of these will have more or less the same range of shapes, and they'll have the same effect of dispersion. So we can try to basically change the order of operations in a typical pulsar search. To correct for the dispersion, we would make the dispersion the first step. And then on all the dispersed time series at trial dispersion measures, we would run an accelerated search, which is the Fourier transform, and then find candidate, and then sift, and then do everything else. Here, we take the dispersed time series, so we don't apply the dispersion initially. We run the fast folding algorithm, and we run the dispersion on each single block. It seems like a waste of resources, but this actually allows us to transform each of the fast folding algorithm steps into game objects that we transform into asteroids. So everything you see here is one of the blocks of the fast folding algorithm. Actually, all of them comes from no blocks of the fast folding algorithm, but from the initial time series, because in this case, we're finding fast radio bursts. And you'll notice that all these asteroids have different smoothness, different dimensions, different colors, and different glow color. All of these map to a different statistical indicator that we've computed in the computer of the gamer automatically. And you'll notice that here there are these two blocks that are a little different from the others. They're bigger, they have a specific glow color. These two, I'd say, are good candidates for a search. At this point, well, there's a whole story. Of course, it's an adventure. You are in a spaceship. You are inside an asteroid field, and you take the asteroids and you put them into some machine where you have instruments to interact with them. And you'll notice here that with your instruments, you are able to make some stripes appear here, and this is actually the signal of a fast radio burst that you're trying to uncover here. For now, we have only two instruments, but we'll have more. Of course, this is still in heavy development. The structure will be a central server or multiple central servers if we need that send a series of simulated and real data. The simulated data need to evaluate the player. So the players that will be more able to classify uncertain signals will be given harder tasks to complete, for example. So there will be a part of training and a part of classification. Moreover, the clients will calculate the statistics for us and will make the combinations of matrices that are needed for the fast folding algorithm for us. So in practice, we'll be doing a GWAP game with a purpose that does citizen science and citizen computing as well. So the computation will not be done completely by our central server or servers. Heavy development, and we're trying to get Horizon funding. We were very well evaluated, but still not much, no acceptance. The Python analysis software was released into a couple of different time series analysis packages and are open source. The C# part will be half covered by proprietary licenses because it's heavily based on commercial products. And there are a couple of papers in preparation, so stay tuned. I want to just leave you with the list of people that have worked to produce this work. Thank you very much.
Thank you, Matteo. And I play big applause for your presentation. And I see in the Q&A actually no question, but I would have actually one. You're representing a multidimensional data with an asteroid, right? And have you considered, I mean, would there any kind of other representation which might be more or less, I mean, suitable for the classification by humans?
Oh yeah, we've thought about many different objects and many different game situations. This was you need to consider many things. One is the affordance of game objects. So the way a game object suggests the way you use it. The other is finding game objects that allow you to change their shapes according to many different indicators. You can put as many indicators as you want. And also game objects that allow you to see a lot of them and point out the ones that are more interesting. So let's say that asteroids were an easy way to achieve this. Future developments might lead elsewhere. Now, this is in demo shape, and I mean, of course, there might be changes in the future.
Okay, thank you very much. And you can actually stop sharing your slides, so we see you for the goodbye. Thank you very much. And our next speaker is Sandor Krok from ESA. He's going to talk about Hubble Asteroid Hunter and exploring the ESA Hubble archive.
Thank you, Pascal. Can you hear me?
Yeah, yes, we hear you. You're on. Okay. Yeah, please share exactly. You can start sharing your slide or do whatever you need to do for your presentation.
Thank you. 1 second.
Yeah, we see the slides. Yeah.
Do you see the slides now?
Mm-hmm. Yes.
Okay. Yeah, thank you, Pascal, for the introduction and for the organizers for running this online conference so smoothly and for giving me the opportunity to present the work that we've been doing last year at ESA. So it's really great to see a whole session dedicated to citizen science at ADASS. So talking about asteroids, I hope to convince you that archival data is extremely valuable and that you can discover many treasures in the data if it is mined properly. And what better tool there is for data mining than the human eye, through the combined efforts of thousands of people. So this work on the Hubble Asteroid Hunter, exploring the Hubble archives with citizen science, would not have been possible without my colleagues shown here, in particular Pablo Garcia Martin and Bruno Merin from the ISAC Science Data Center. And of course, the 11,000 volunteers in the project itself. So our main motivation for this project is to facilitate the discovery process in space science missions and to better explore the rich Hubble archives. And in fact, most of the publications nowadays from the Hubble Space Telescope are either archival or partially archival, as you can see from this plot. So we are now slowly moving in this era of data-driven astronomy, where the majority of science is done with surveys and with archives. And in the 30 years of observations, Hubble produced hundreds of thousands of spectacular images of rich clusters of galaxies, of nebulae, places where new stars are born, but also where massive stars die, such as this gorgeous image of the cosmic reef here in the center of the image. But occasionally, these nice images made by Hubble that you see are ruined by objects much closer than the targets Hubble was observing. And you can see in this nice long exposure of the Hubble parallel fields of galaxy cluster Abel 370, 20 streaks made by asteroids situated in the foreground. So actually in this image, there are a total of 7 asteroids numbered from 1 to 7. And the reason why the asteroid appear multiple times is that it moves between 2 consecutive exposures of Hubble. So this is a long exposure of Hubble. And the trails that you have seen have this exceptional characteristic. So they appear curved in the Hubble images. And the reason for the trails being curved and not straight, as perhaps one would expect, is because of the parallax introduced by the motion of Hubble around the Earth. So typical exposure of Hubble is 20 minutes, whereas Hubble goes around the Earth once every 90 minutes, which is enough to imprint this small displacement in the shape of the trails. And it is easily resolved by the high resolution imaging of Hubble. And multiple images of the same asteroid can appear in the image because Hubble usually takes consecutive exposures. And once upon a time, actually, some astronomers called these asteroids in these images the vermin of the sky because they interfered with the observations. But asteroids are amazing objects to study on their own. They are the leftover from the formation of our solar system some 5 billion years ago and contain information about its origin and the pristine material that existed back then. There are over 1 million asteroids known now. Most of them are in between the orbits of Mars and Jupiter in the main asteroid belt. But some of them get displaced and can move closer to the Earth, and we call them near-Earth asteroids, which are of course rarer, but much more important because of the remote possibility that they might be colliding with the Earth in the future. So the motivation for our Citizen Science project is to identify the asteroids in the Hubble images and to characterize them. So for this purpose, we built a Citizen Science project based on the Zooniverse project builder. And this project builder allows us to build projects quickly through a friendly interface and to promote the project on the Zooniverse platform to a large pool of volunteers. So this is the main interface of the project, accessible at the following link. And what we are showing people or volunteers are composite or drizzled images from the Hubble Space Telescope, the Advanced Camera for Surveys, and Wide Field Camera 3. So the data taken by Hubble in the last 20 years. And since the images were quite large to inspect in one go, considering how small these trails are in the images, we split the images into 4 different quarters, like the one you see here. And this is what we show to the volunteers. So the volunteers had to answer a simple question whether an asteroid is present in the images or not. And if it is in the images, then mark the beginning and end position of the trail so that we can identify them and we can convert them to astronomical coordinates. So we launched this project just ahead of the International Asteroid Day on the 30th of June, 2019. And we distributed, the project was advertised widely in the ESA social media channels and also on Zooniverse. And it gathered tens of thousands of classifications in the first days. And we're looking for new things to do. So citizen science projects were indeed a good scientific and educational resource for people. For example, many teachers use Zooniverse project as an online resource. But it's also a place where people can look at nice images from the universe, as you can see from the reaction of this volunteer, saying there are lots of beautiful sights in the universe, especially now that I can't travel to see any earthly sights except those in my immediate neighborhood. Now, in total, we had 11,000 volunteers, over 150,000 images classified, and 2 million classifications during 1 year. And here's a plot showing all the volunteers in the project and their contribution, with the size of the boxes corresponding to the number of classifications. There are a couple of super users, we call them, who classified many of the images. Now, using the volunteer classifications, we identified the images where more than half of the people said there were trails present. And with the science team, we inspected the images. Now, the reason for further investigating these images is while we're used to the beautiful Hubble images on the internet, those are processed images. So the original images contain artifacts, which can be confused with asteroid trails. For example, occasionally images have these badly subtracted cosmic rays or arcs from gravitational lensing effect that is targeted in many Hubble images, and these resemble asteroid trails. There are also satellite trails that cross the entire image, and these are satellites in higher orbit than Hubble. So we inspected the classifications and identified 1,500 good asteroid trails, like you see, like the one you see in this image. With the yellow point, you can see the individual markings of the volunteers, and with the white circle, you can see the aggregated marking using the clustering algorithm HDB-SCAN. And here are some more examples of the trails that the volunteers identified in the images and the markings. They have this crazy shape. Some of them are curved, some of them are S or C shaped, depending on the motion of Hubble and of the asteroid. And you can actually recover these asteroids moving in the roll frames as well after we identify them. And quite early on the project, one of the volunteers, Melina Teveno, found this nice asteroid trail photobombing the Crab Nebula in a rare cosmic coincidence. And she created this nice color image of it and sent it to us. Some of the volunteers also found this nice image of a dwarf galaxy and two asteroids crossing paths in the foreground, which again is pretty rare to have two asteroids on the same line of sight at the same time, like in this image. And many volunteers went beyond simply classifying images. The project has an active forum where people can go and post nice images, ask questions to the science team, and even do their analysis. In this example, one volunteer explained the process in which they identified the asteroid in the image themselves using ephemerides from the Minor Planet Center. So going on to some results, in total, out of the 1,500 trails, we identified 500 known asteroids based on the ephemerides in the Minor Planet Center database. So this is the largest database of small bodies. So these are asteroids that match their predicted position within 3 arc minutes. You can see some examples here on the right-hand side. Most of them are main belt asteroids and have magnitudes between 20 and 24, so they're pretty faint. Now, one of the biggest advantages of Hubble is that it is sensitive to fainter asteroids than instruments from the ground. But still, about 1,000 of these objects are unknown objects, or objects which have a large orbital uncertainty. So it is entirely possible that these are new objects. Since Hubble, as I said, is sensitive to small and fainter objects. And we think that there are thousands of asteroids, especially in the main belt, that have still not been discovered. So we are further scrutinizing the classifications. And since we know the orbital parameters of Hubble, the shape of the trail can tell us about the distance to the asteroid based on the parallax. And this is still something that we're working on to identify the missing 1,000 asteroids. Now, one of the biggest advantages of having people look at the data is that we can benefit from the power and intuition of the human brain. When we first designed this project, we did not realize that the strong gravitational lensing that were imaged so frequently by Hubble, this phenomena, these small distortions in tiny arcs caused by the bending of light around massive objects, can sometimes throw people off, the volunteers off, and they identify them as asteroids because they look like curved trails. So they were asking, what are these objects? A few weeks into the project, we asked the volunteers to tag these objects as gravitational lenses so that the science team can filter them out when we analyze the results. And when we analyzed the results this summer, surprisingly, we realized that we found 200 new gravitational lens candidates. Some of them you can see here on the right. I call them candidates since they have to be confirmed spectroscopically. And these were not targeted observations, but serendipitous findings. And this is great, since so far only about 1,000 strong gravitational lenses are known. And this serendipitous discovery would probably not have been possible with automated methods, or perhaps even by astronomers, since we would have probably ignored them if we were looking for asteroids. Now, another surprising discovery is that the small but non-negligible fraction of the Hubble images contain satellite trails that go across the entire image. So you can see here on the right-hand side an example of a broad satellite trail that is out of focus, probably a satellite that passed quite close, tens of kilometers away from Hubble. There are also satellites that are flickering, or satellites further away, possibly on the way to a gestationary orbit, showing the same parallax effect as for the asteroid trails. And also an image with 3 satellites. And we can work on this exercise and perhaps worry that in the future the number of satellite trails will only grow and impact the Hubble observations. So the satellite trails not only impact ground observations, but also space observations in low Earth orbit. And finally, if I have 1 or 2 minutes left, I would like to advertise some ongoing work that we've been doing in collaboration with Google. So we have been using their object detection algorithm, AutoML, trained on the volunteers' classifications to automatically detect asteroids and satellite trails in the images. Now, in the last few years, there have been many advancements in computer vision with deep learning algorithms based on convolutional neural networks that are not only able to classify objects, but also detect their positions. Such as this object detection algorithm being able to identify cars and people and traffic lights in the images. So we apply this algorithm to the Hubble images, and we're able to detect the asteroid trails with a precision of 80% and a completeness of 60%. And using this algorithm, we classify the archive, finding new asteroids and satellite trails in the Hubble images that people either have missed them or they haven't been shown a certain data set. Now with the Google AutoML, we were able to train the algorithm in only 3 hours of world clock time and classify the entire archive in just 7 hours. So only in 10 hours in total. A task which has taken the volunteers 1 year in total. It took us 10 hours. But of course, we already had very good labels for training for 4 different objects. So asteroids, satellites, cosmic rays, and gravitational lens arcs. If you want to hear more about this project on automatically detecting asteroids in the images, you can follow this link here on the right. So some takeaway messages. Look at the data if you can. Sometimes unexpected things might hide in there. We went to search for asteroids and found gravitational lenses, satellite trails, but also some other unusual morphologies like collisional rings that I didn't have time to talk about. The next take-home message is that one astronomer's trash can be another one's treasure. Hubble, with its small field of view, was not designed to observe asteroids, but the fact that it is in space and can reach fainter magnitudes can offset this. Thirdly, citizen science has proven to be an efficient method to explore large data sets, as me and others have shown during the session. There's just something about the human brain that is able to go beyond what is required and spot unusual things in the data. At the same time, like you've heard probably many times at ADASS already, with upcoming missions such as Euclid and LSST, data will increase exponentially, but humans will not. So we need humans and machines to work together in the future. And we need artificial intelligence methods to scale up the power of crowdsourcing. And for this, we need many and good labels to be provided for by the citizen scientists. Thank you.
Thank you very much, Sandor. And we have already 2 questions. One question is, can you find slow-moving trans-Newtonian objects?
Yes, so these are actually harder to find because the exposure time of Hubble is only 10, 20, 30 minutes. So it's not very long, and they don't produce such a long trails in the images. As I said, most of the trails that we identify are from main belt asteroids.
Okay. And another question is about the Asteroid Hunter project. You mentioned super users. Do you know who are the super users? What age, what occupation? Is there a certain type of people for super users?
It's varying actually. So we are in touch with the super users because they obviously classify a lot. They comment a lot on our project forum talk, and it's actually a range. So I'm collaborating now, for example, with one of the super users who is about 70, and he's a retired engineer in Paris. So it's actually, yeah, as I said, a wide range, but people who are really passionate about it, and they go beyond the scope of the project. So they don't only classify, but they actually go on and use different surveys. They look into Simba, they look into NET, and they are actually, I would say, expert citizen scientists.
Okay, thank you very much. There are no more questions. Thank you very much, Sandor. And our next speaker is going to be Sergio Pascual from the Complutense University of Madrid. Sergio is going to talk about citizen science with the TESS photometer network. So Sergio, could you please?
Hello.
Yes, start your video. Hi, Sergio. and
Hi. Share my screen.
then start sharing your slides. And there was one more question actually in the Q&As from Peter Skoda, but I would propose Peter to write the question in the talk so that Sandor can answer in the talk channel of Discord. Okay, thank you, Sergio. You can start your presentation.
Hello, good morning, good evening, good afternoon, everyone. I'm going to talk about a little bit about the test photometer network. I'm the speaker, but this is a team effort from of people of the Universidad Complutense, Universidad Politécnica de Madrid, and also collaboration with amateur astronomers. The photometers are dedicated to the problem of light pollution. Light pollution is, as I have defined there, excessive, poorly directed or unnecessary artificial light at night. We, our astronomers, are well aware of the problem of light pollution because it destroys the dark sky that is our way of working. We need a dark sky to view the stars, but this is not the only problem of the light pollution. And in the last 20 years, more or less, people from other communities have come also to the problem of light pollution, because this light pollution interacts with the night ecosystems. It disorients insects and other animals and affects its way of life. It also affects human well-being, produces insomnia and other metabolic disorders. So coming from different disciplines, people from biology, human health, and astronomers have to fight against this common problem, the light pollution. Astronomers have a long history of using sky brightness as a measurement of the quality of the night sky. We wanted to have our observatories as far as possible from intense light sources. So we have a long history of measuring sky brightness. And sky brightness is one of the key parameters to measure the light pollution. Light pollution is not only the sky brightness. It includes also the difficult problem of the light diffusion in the atmosphere and the position of the different luminaries. So it's not only the sky brightness what we are interested in, but sky brightness is one of the key parameters and is a proxy for light pollution. Measuring the sky brightness with a photometer pointing to the zenith is a first estimate of the light pollution, and it tells us how light pollution affects a given location. It is possible to obtain statistical results if we have a long series of data of different nights. I have here two plots of the measurement of sky brightness in two different nights in two different places, one in Spain and other in Portugal. The plot on top is a typical clear night without clouds. As this is magnitude, dimmer magnitudes correspond to larger numbers. So in the middle of the night, we have a plateau corresponding to the dark sky. On the other hand, in the bottom, we have a typical night with clouds. We see that the night brightness changes a lot along the night. So what we wanted, we would like to have a long series of data for a given place and a lot of places to have different atmospheric conditions so that we can research how the light pollution affects different locations. To do this, we need photometers pointing to the zenith, for example. These plots are made with the SQM photometer, that is a tool that is used a lot in this kind of experiments. we would like to go further with photometers. Here enters the Stars for All platform. It was a project funded with the Horizon 2020 European project, and its idea is to encourage citizens to be aware of the problem of light pollution and promoting dark skies. Of the several projects that were and the initiatives that were under this project, I'm talking about TESS. Also, this is not funded anymore. We still are progressing with several projects. TESS is a low-budget photometer designed at Universidad Complutense with the idea of being able to work unattended without a dedicated computer. The SQM photometers usually need a computer attached to them so that the data can be extracted and stored in other place. This photometer is designed to work unattended. The specs are open both in hardware and in software. Once that it's set up, it only needs your local Wi-Fi and an USB for power. Once that is set up, is intended to work alone. Here I have a description of the contents of the photometer. Basically, it has a PCB board with a sensor that is not sound, is a photodiode. It's the same photodiode that is used in SQM. We have a collector, a dichroic filter, and a Wi-Fi module, a near-infrared sensor used to detect clouds. Compared with the SQM photometer, the sensor is the same, and there is a difference in the filter. The filter of the TESS photometer is more extended to the red, so that this photometer can cover the high pressure sodium lines that are around 600 nanometers. The SQM only covers that region marginally. So this photometer is prepared to work with light pollution. As I said, the specs are open. So for example, we have uploaded in this webpage Instructables that is very popular in the do-it-yourself community with a long description of how to set up build your photometer. Of course, we have also uploaded this in Zenodo with a manual to do the same. If you follow these instructions and you do it yourself, you can have the photometer. The only step that is still required to perform by us is the photometric calibration. We compare it with an integration sphere with a master photometer, so that every photometer is calibrated. But apart from us, everything can do by a person interested in this. So how do you set up the photometer? As I said, you plug it in with a USB, and once that is online, it opens a access point with a web page. You connect to the web page where you set up the location of the photometer and the Wi-Fi password. You save it, and then the photometer attaches itself to your Wi-Fi and starts to send data. And that's all. If you don't want to do any more, that's all we need. If you instead want to connect access to the photometer, there are several applications, Android or Windows, that you can use to locally connect to your photometer and see its data. This is, for example, the Android application to connect to the photometer. But this is not the main mode of the photometer. The photometer is designed to work unattended in the remote mode. In remote mode, the photometer is connected to your Wi-Fi and is using MQTT, the protocol designed for Internet of Things, to send data to MQTT broker that is set up in our institution. The protocol, the MQTT protocol, works in a publisher-subscriber model. The devices are publishers and they are sending data, and you can build your own application that subscribes to the broker, retrieves the data, and do different things. In a very basic model, for example, you could subscribe to your broker and listen to it and get your data without having a particular application, or get the data of the photometers nearby you. But you can build dedicated applications or large applications. One application that we have built is a panel, the test dashboard, that contains the information of all the photometers. Now here I'm going to try to open the actual dashboard. I know this is dangerous, but I'm going to try. Yes. So in red, the photometers in red are not configured, or they have problems, so they are not sending data. The white ones are sending data. So I'm going to zoom into Spain, that I know better. And I'm going to open a particular photometer. This one that I know that produces very good data. Is loading. Okay. So first of all,
2 minutes, 3 minutes. Huh?
How many? 3.
Yeah, about 3 minutes.
Yeah. Here we have a plot of the last night, and here we have different panels that contain a lot of information about the photometer. Here we have a series of previous nights, information about the clouds, for example, and this is the observation of the previous night. I'm going to open it here. For example, if you want to retrieve your data, you can always go here, your data for your particular photometer, and follow these instructions to download your data, or you could go to Zenodo, for example, where we are uploading all the data month by month in a CSV file. We are also uploading data to this place, B2Share, that is a new platform for sharing data in the European Union, and each product gets a DOI, so it's fully citable. We have also uploaded this to the Spanish BO, and they have built this nice application so that you can search here and produce plots of your night, or download a CSV file also. I'm finishing. We have a working network of photometers, and this is set up. Here we have one of them set up by interested citizens. We have 139 photometers sending data. It's interesting that not everyone with a photometer is keeping it online. So sometimes they plug in, they configure it, and they don't bother anymore. They don't check that the photometer is sending data. Sometimes it's kept in a drawer. So we go to a meeting and we give several photometers to people that are interested in installing them, and they don't do it. But the installed photometers are a very valuable source of data to monitor sky brightness. If you're interested, you can go to the webpage and follow their links to obtain your own photometer and install it in your at home or in your institution if you want. I don't know if I have 1 minute or something. We have other working projects also. Portable photometers is something TESP that you can have in your pocket, and clicking a button, you get a measurement of the sky with it has a small display. And TAS, for example, is a test photometer mounted in a automatic mount, a robotic mount that can make all sky brightness map. It moves around and maps the sky in all directions. And I'm not abusing my time anymore. Thank you very much.
Thank you very much. And Sergio, in the Q&A channel, I have one question, and I think due to time, I will take only this one. Then there will be questions for you in the talk channel of Discord that you can answer after the talk. But the question from Alex is, are all photometers located on roofs of private houses? Is the orientation of the photometer important?
The photometers are, some of them are in roofs of private houses, but or others are in the roofs of universities, even in hotels. There are several hotels, places that use night sky as a way of getting people. So they want to have this is another activity that we have in the network. The orientation is important. The photometer has to be oriented towards the zenith. It's not necessary that is exactly oriented vertically, because the field of view is like 17 degrees. So it's not critical that it's perfectly oriented, but it has to be oriented towards the zenith.
Okay, thank you very much. For the other questions, I will let you, Sergio, answer in the talk channel of Discord. And we are now moving to the next presentation, which is a focus demo by Cedric Felmy from F52 Technologies. And Cedric is going to present arcsegon.io. So Cedric, you can maybe start your video. Yeah, we see you. You can start your mic, turn on your microphone.
Should be okay.
All right, yeah, we hear you, we see you. And you can start sharing your screen for the demonstration, which will last about 30 minutes.
Yes, thank you very much. Good morning, everyone, or good evening. I don't know. Let me share my screen. Okay. I'm very happy to participate to this conference. Thanks very much to the organizer to allow me to present arcsegon.io. It will be a demo, and I hope to not experience the demo effect, but it should be okay. arcsegon.io is a project. It started with as a personal project, and now it's a fairly extended online platform for astronomical observations. I removed the citizen science description of it, because compared to the last talk, just the previous talk, arcsegon.io is not a collective effort of citizen science. It's mostly a platform that can be used by a lot of other people everywhere. But I will describe everything. Just a quick presentation. I used to be a real astronomer. In the past, I've been doing astronomical observations in various countries: Switzerland, Canada, Chile, and France. I spent a lot of time in Chile, especially in La Silla Observatory, where I spent more than 360 nights. And since 2010, I switched to a private sector and worked as a software developer in various startups and companies. And today I'm Vice President Engineering in Azeta Nanographics. And all these years as astronomer taught me a lot of things about software. And then I switched to the private sector, and I realized how much I was still needed to learn to be a real professional software developer. And I enjoyed it a lot. So my professional specialization is actually software industrialization and engineering. So I help team to deliver software in an industrial way. A little bit of history for arcsecond.io. It all started in 2003 with Mac OS, or at that time it was called OS X Tiger widgets. It started very small with tiny widgets like that, providing just the basic times values. But in 2010, these widgets were transformed into a real native macOS app called iObserve. Of course, the very first version of iObserve was not that sophisticated, as you can see in the screen, but this is the current version of iObserve. I hope to have some of the iObserve users in the audience. I can see you. But iObserve was, again, a personal project. It's still available in my App Store. And the main idea is simple. It's the app I wish I had when I was at the telescope. So it's nothing really revolutionary. It's a lot more software engineering than actually algorithm or mathematical difficulties. But the main thing is that it's all at the same place, and it helps you prepare observations. But iObserve is what we call a heavy client. So everything is inside this app, all the connectors, all the transformations, all the storage and everything is handled in this heavy client. So it has some advantages and it has disadvantages. Once upon a time, there were an iPad version too, but that's another story. Arcsecond.io is the direct and much extended evolution of iObserve. So that's it. And the main goal was to bring this particular view with air mass curves to the web, because it was that was the main pitch at the very beginning. Because it was limited to macOS users, and even if I know that there are many Mac users in the astronomer community, still there are many others. So I wanted to bring this to the web. A little bit, point on a different philosophy, the Apple versus Unix philosophy. Arcsecond.io is clearly designed with more the Apple philosophy, in the sense that we recognize the value of the integration. That was the philosophy of iObserve too. I love also the Unix philosophy, which is do only one thing and do it well. That's not really the case for Arcsecond.io, which I think brings a lot of value because it is all at the same place. But of course, it's a bit difficult because there are many things to do. But I will let you judge the quality of the results. But that's the philosophy behind Arcsecond.io and iObserve. Just a quick slide to explain a bit. Arcsecond.io is actually a software system. It's a bit more than just a software. And I emphasize a bit this part of software system because actually that's make things a bit more complex. But it's actually very, very interesting, and I enjoyed it a lot to build this. And actually, it's my best business card in the software world. So the main 2 points of Arcsecond.io is from one side API.arcsecond.io and the other side is www.arcsecond.io. The first one is the data. It's a pure REST backend. I am rather strict on applying the REST principles because I've seen many REST APIs sometimes in various astronomer website, but it's REST is not just making JSON. And so API.arcsecond.io has more than 100 endpoints. It's built with Django 3, Django REST framework. It's all Python with thanks to being written in Python. I can easily plug very important and community-powered libraries like AstroPy. I use a little bit of AstroPy, not much, but still they are very useful things. AstroPy, Celery, Postgres, the usual, I would say, standard Python backend stack. We use Amazon S3 for storage, and of course Unicorn, UVcorn for the server. Its internal architecture is what I call a microlit. There's a lot of fuss and a lot of discussions about making a monolith versus microservice in a cloud software world. But I think a monolith which is well decoupled can be called a microlit and enjoy the advantages of small modules, but the easiness of deployment of a monolith. So it's a microlit. It's deployed on Heroku, which is a PaaS on top of Amazon. Amazon is a IaaS, infrastructure as a service. Heroku is a PaaS, platform as a service. It provides many high-level services and makes things a lot easier. And basically, it let me concentrate on development and not the operations. And I will speed up a little bit because otherwise we won't have time for a demo. So that's really the main foundation. API.oxagon.io is the main thing on which I can build other stuff. And the main usage of API.oxagon.io is www.oxagon.io, which is a single page application written in Vue.js and using also libraries and astronomical algorithms, which are all open source. It's also deployed on Heroku and everything. But of course, that's not the only possibility to use API.oxagon.io, which can be used by anyone in different ways. It's opened. Some endpoints are private, some endpoints are public. But it's there to be used. I've written also a Python CLI, which is can be used as a command line interface. I will show you, and also a Python module. And last but not least, OrtCloud, which is the simplest tool that can be used to upload data to Oxagon.io. I will show you how it is used by observatories. Will be used by observatories. Just a quick thing, the only way to build such a software system is really to industrialize everything. So it means that software quality has top requirement. It means unit test, unit test, unit test, unit test. So a lot of unit tests everywhere, as many as you can. Also integration tests and everything automatic. It must be automatic linting, automatic testing, automatic code quality, security checks, automatic deployments. I mean, that's the only way to reliably produce software in a cloud and otherwise to make sure that you can sleep well and not worry about bugs. Because when it's online 20 hours a day, 7 days a week, and you have another job, it's important to be relaxed and know that it works. And then, of course, monitoring as well when it's online. So a demo. You can try yourself www.oxagon.io. Of course, you're free to try. Oxagon.io has a public and free part, and of course, private part. It's a commitment to have always a free and public part that can be used by everyone. It's actually already used in some classrooms. I'm very happy with that. So we'll, of course, keep a useful part of Oxagon.io as a free part. But of course, there are some paid services because we want it's a real service with real servers, and it's all funded personally for now. So that's it. Let's move. I hope you can see my screen. Let me know if it doesn't work.
We see your screen, yeah.
Okay, wonderful. I will reduce a bit. Niet 8 seconden tire. This is how it appears. So you can see that there is quite a few things already built. And let's start with I observe. So I observe. You can try. You can actually choose any place on Earth to use I observe. You can use also the there is a built-in observing site encyclopedia inside Oxycontotayo. So let's choose, say, Lacia and open I observe. That's it. So that's I observe. I mean, that's the macOS app basically rebuilt on the web. As you can see, so you have air mass curves with tracking. You can choose, of course, the date you want, and you have star tracks. You can follow star tracks along the night. Okay. You have. I should have opened. Actually, I should have chosen. Zero panel. Yes, choose panel. That's it. To show you that there are also horizon masks in some observatories. So if you choose UT1, for example, I mean, there is a list of horizon masks which can hide part of the sky. Oops, there is a little, yeah, you're right. So you can see that depending on your targets, yeah, it can be hidden by some of, I know that the J6, I think is very, yeah, the J6 is probably the worst. There's a little glitch of drawing. You can see that you have the shadow of various observatory domes. We are on the plateau of Cerro Parnal, so it can have an impact on your observations. Of course, there are many customization possible to just see what you want. You can choose multiple curves. You can change, of course, the colors. That's all the I observe classical. Oops. Classic. Little bug. It's supposed to disappear. Okay. This stuff is supposed to disappear. I've made an update recently, and okay, because I rewrote all these components, of course. But okay, that's the demo effect. Of course, there's a little thing, but that's the idea. What I wanted to show you is also that you can actually we'll leave this with this small thing. Wait, I want. Oops, no, I wanted to show this. Yeah, and you can show the Starlink tracks. So it takes a bit, yeah, of time to be computed and show off. Yes, no. I would be surprised to not have any Star Trek links on that day. Of course, that's the demo effect. It was working yesterday. Okay, I will fix this. You have normally up to 2 seconds to drawing of Star Trek links across the sky. I'm a bit disappointed, of course. Not showing. Strange. Okay, I can see it's difficult. You can see there's still a little UI glitches. Of course, JavaScript is not as easy language as Objective-C. You have access to Aladdin and publications related to these objects. Of course, you can import objects by coordinates manually or import from files. So you can provide actually a list of targets. It will import. You can import exoplanets from the whole exoplanet.io catalog, and as well as target lists. Target lists are things that can be shared and can be private or public. For example, we provide the Messier catalog target list. This is the whole Messier catalog with 110 targets. So if you want to prepare iObserve and use this target list to say to make a Messier hackathon, for example, then you can use this target list. So that's the main iObserve. That's the main Pro tool. That's our section of Pro tools. iObserve is the flagship Pro tool we have, but there are some others like Transit Finder. Sorry. So it's built on the list of exoplanets which have transits. So the idea is to be able to predict and predict when exactly a transit will occur and in what conditions. So here we are in the Lassia observatory. We choose 55 CNCE. So you know that the transit is in 10 or 20 minutes. Yeah, 18 minutes and 57 seconds. So you have the various information about this, and you can filter in various way the transits. We make sure that every time you choose another transit, the URL change. That helps actually make a bookmark or share a URL of specific transits to be shared, and you end up right away into the right page and configuration. So that's another Pro tool. We have a Standard Star Explorer, Standard Star catalogs.
You have about 5 minutes.
Okay, thanks. Standard Star's catalogs have been spread around in many different websites and often in bad formats. Astronomers tend to create web pages, but web pages are not easily consumable by machines. They are easily consumable by humans, but sometimes catalogs must be used by machines. And of course, you have many catalogs in the CDS in Strasbourg, but the Standard Star was different. So we actually open sourced and took all these catalogs and made available in a consistent way in GitHub. It's all open source. You can fix and correct and see and everything. There are all the origins where all these data come from and can be used here. So you can put coordinates or star, whatever, and it finds you the standard stars, the closest standard stars to this object in all the catalogs. Okay, so that's another Pro tool. We have yearly visibility. So the idea is to see the visibility of, say, a target somewhere. You can choose where, and somewhere on Earth. So you have the January on top, December on the bottom. So you can see the length of the night changing and the visibility depending on the threshold of altitude you can choose here. That's another Pro tool. Times converter, distance converter. That's the thing of iObserve which have been improved, rewritten in a modern way with open source algorithms. It's all available on GitHub, and there are more things than in IOTA. And we have the, of course, the Observe Insight encyclopedia, which is necessary to work. We have telescopes, satellites. I want to show you also the activity screens, because we monitor. Okay. Yeah, live map. We monitor great observatories, what they observe, and we scan this and provide activities. We call this activities because it's observing activity. So we scan ESO, Gemini, HST, and SWIFT satellites for now. We intend to provide to scan more stuff later on, but that's the idea. And you can actually subscribe to these activities. For example, if you have, if you take the Mauna Kea Observatory, that's the page of the Mauna Kea Observatory. You can see that you have the map, the various telescopes, and the activities, which is the various things. So you can see that we detect the activities, the people, the program, the instrument, everything has been normalized, so it can be easily accessed and linked. And funny stuff, you can actually, oops, this way, you can actually create your own activities. It's designed to be an alert system that can be used by small observatories actually to create activities and publish activities that can be then subscribed on by other people. So let's say we create real demo test. So then using the ArcSecond CLI Python module, we create an activities for the telescope in a Mauna Kea. So trust me, that's the UID of the Mauna Kea. And it takes just a bit of time to appear here. Unfortunately, I don't think we have enough time. I hope it will appear. But just to show you how it works, and the thing is that I personally subscribed to the activities of Gemini North in Mauna Kea, so I received a mail. So you see that an observation is running with Gemini North, published by Cedric just less than 10 seconds ago, and you have an activity page you can actually open. Oops, it will open somewhere else. That's it. It will open Safari, etc. So you have a page with the activities. Yes, real demo test. That's it. And last but not least, I will finish with that. We have portals for small observatories. And I don't have time to show you, but we have a space for collaborations for small groups of astronomers to share data, to share target lists, to share night logs. We are preparing night logs. This is, for example, dataset tables of an observatories that we work with in Chile. So they are uploading their data to their own portal. You can see that they have their own subdomain. So that's something the main idea behind all this is to bring observations to the cloud. That's it. So we want to help small observatories. We know the big ones have their own stuff. We want to help small observatories to bring their observations to the cloud with the benefit of having something professionally developed and supported with modern tools. And that's it. If I have 1 second, I will just show
just
you.
1 second yet.
1 second to show you the collaborations. We have a collaboration space here where you can share. That's a collaboration. You can share target lists data sets and night logs. And this is a space designed for small collaborations to help them prepare observations. Often I've seen various people working for the same projects. It's not always easy to share what they observe, how they observe, and to share the data. Here, you can share data. It's stored on Amazon. It's cheaper than Dropbox, at least for sharing. And because the storage is paid only once, and we prepare night logs also to be shared soon live. That's it. I will stop here. There are too many things to share.
Okay, thank you very much, Cedric. Thank you very much. So thank you. We have a question from Danuta Sosnowska, and that's about what about the confidentiality if you upload your data about your observed object? What about the confidentiality of the data and about the security of the data? I think the security is answered on your website. I was checking, but maybe please you can answer on both confidentiality and security.
Yes. Your data is always yours. Your data is stored on Amazon on private buckets, encrypted, private by default, with all the switched privacy and security on. It's very safe because it's Amazon S3, which is basically half of the internet. As for the access of this data, it's going only through ArcSecond. You cannot access your data otherwise. And every user has his own slot. Actually, you cannot access the data. It's very much organized, and otherwise everything is encrypted. Of course, we have professional certificates. All the communications are encrypted, even between the CLI and the Python module and the backend. As soon as we can, we intend to pay for various pen tests, what we call, to validate. For the moment, ArcSecond.io doesn't have enough resources to actually certify the security of the data as real companies does, but we hope to make it as soon as we can to certify the security of the data and the system by external sources. But this, otherwise, we have taken everything that we can to secure the data so far. I hope to have answered.
Thank you very much. There are a couple of questions on the top channel of Discord, which I will let you answer later. And I would like to give a big applause again for all the presenters of this morning's session and all the participants who then made this session so lively. And I wish we could have a drink together at a coffee pause or so, but this is a virtual conference, and we are going to proceed with the Birth of a Feather session on reproducibility in astronomy, and it works on my laptop. Why so? Let then the room manager set up the panelists for the both session. So who is? Yeah, hello. So Mateus is going to lead the both session. Mateus, could you start your video?
I'm trying.
So I have all the panelists. Mateus, you're in. Yeah.
Okay. Great.
I will stop mine. You can start.
Can you hear me? That's the first
We can
one.
hear you, but we still don't see you.
Yeah. This is weird because I've tested it on other stuff and video worked, and I also have sound coming, because if you can hear me, that means that the camera is recognized properly, because I have sound coming through my webcam, but
Right.
the Zoom is refusing for the video to work.
Yeah, I had a similar problem this morning, and I unplugged and plugged my camera again.
Yeah. So, you know, so that's an already good start for the subject of reproducibility.
All right.
it worked with something else, but not with Zoom.
Can you try maybe sharing your screen, or you might have slides to introduce a session?
Yes, yeah, no, I do have slides. So is it okay if I try restarting Zoom quickly? Would that be okay? Just literally 30 seconds.
We don't see the screen sharing. Okay, yes, I was informed that Mateus is restarting Zoom.
Yeah, I'm back. But
you're back, all right? Yes.
But it's still refusing to do the thing, unfortunately. Oh, okay. Yes, okay, it works. Right, okay, right. That's my bad. That's my fault. If you all can see me.
All right, we see you.
Yeah, that's my fault, because I was testing it. I had the software I was testing it with open at the background.
Big applause for you coming to the conference.
Yeah.
All right.
Now you should also see my slides now.
And we see your slides.
Perfect.
So I will mute and let you proceed.
Yeah, thank you. Sorry about that. That what happens when you test stuff. So welcome to this BOF session. So it has a very long title officially, but what I would just like to call it is reproducibility in astronomy. And I think it's a fairly important subject. It's a very important subject. So it's only me on the panel. So what I would like to encourage everyone to ask questions. It's designed so I've got slides, but it's designed in the way so that we can have as much as possible through Zoom a conversation that that we can exchange ideas, because I think it's a very, very important subject, reproducibility, and indirectly and directly it's coming up in talks and in BOFs that we've already had, and we'll have. If you look at the list of BOFs, there is a lot of about citations, archiving data, standardization of data, data formats, that all works in tandem really with reproducibility, and all these things together sort of ensure reproducibility, make reproducibility easier. So this is more of like an overarching BOF of how we approach the reproducibility and how to go around it really. So as I said, it's very important. So I encourage everyone to be active in the discussion. Please, ask questions. I'm monitoring, I'm lucky to have two screens. So I've got presentation on one, and I'm monitoring Discord and all the lists inside. So please feel free to ask away, ask all the questions, raise your hands, and I encourage everyone to ask questions. So there are no silly questions, there are no stupid questions. If you've got a question, please ask. If you see something that you disagree with, raise your hand, say that you disagree, or in questions panel, say that you disagree. If there is something that you really resonates with you, you agree, do the same. So please be an active participant. So it's a long word, reproducibility, and I bet there is somewhere on the slide that I misspelled it. But what does it actually mean? So before we actually start talking about reproducibility, we need to really talk about what it means. And over the last few years, when I get really interested in the subject, I've started talking to people, and I started talking. The main question is, what does reproducibility mean to you? And you answer multiple people, you answer 10 people, and then you don't get the reproducible answer. See, it's a difficult word. And the most common theme is it will depend on the field. So depending where you're coming from, the reproducibility will mean something else for you. Might depend on your personal preferences. So often there is a situation that even within the same field or in the same working group, you've got people with different experiences. Someone could have been developing code for 30 years. Someone could have been working on the code for 2 years, and someone might be just came from finishing undergrad degree, person who's never done any code before, and starting, to write first lines of code in Python or any other language for the master's thesis or PhD. So for each of these personal reproducibility may mean something else, but it also may, kind of connected to the field, but depending where you are in the processing chain, and we see by the already talks given, we've got a range of people attending the conference. So we've got people, what I would like to call, from all the areas of the processing chain. If you build hardware, reproducibility may mean something else, and you might have different criteria for reproducibility. If you build an LNA, for example, if you pass some signal through your NLA, you want to get an output within certain limits. Every time you pass the same input. Do you write software or manage software? As a software manager, reproducibility may mean something else to you than when you write software. Or are you the person that runs the experiment, who points the telescope and looks at the data and collects the data, and ultimately reduces the data, processes the data? Reproducibility may mean something else to you. So as I say, your mileage may vary. So first call to all the people listening is, I would like to hear, what reproducibility means to you, and which fields are you coming from, and are there any sort of requirements imposed by your field? on the value of reproducibility, because there are certain fields that may have some of the requirements slightly to a lesser extent than others. So why do we really need reproducibility? And it's kind of an obvious question with an obvious answer, so that we can really repeat the experiments and reproduce the experiment, reproduce the results. So reproducibility is so that we can reproduce the results. It's a closed circle in this case. But again, it's very connected to, I think, the first slide, to what it actually means to you. Will dictate what you need it for. So if I'm a software administrator and a software manager, my meaning of reproducibility might be that I've got a nice package ecosystem, and every time I deploy it on a new node or have to reinstall the node, I've got the reproducibility. I can reproduce the software ecosystem on every node, on every compute node, independent, in short amount of time with as little downtime as possible. And every time I do it, it's ensured that it's exactly the same most of the time. And I need it because I know that I've got users that I have to provide for, that someone depends on this code. If you are a scientist that produces the data, that produces the results. Yes, it's even hard to reproduce the word reproducibility. I've been saying it so many times, and I still can't. There is even a worse word coming up later. So if you're a scientist, reproducibility might mean something else to you. That maybe every time you run the pipeline, you get at least similar results, and so on. There is also one part of why we need reproducibility that I think is often not neglected but put to one side. But I think as time goes by, we should be more and more aware of, and that is maybe geared towards mainly software developers and scientists. Is we've had a lot of talk about the citizen science projects in previous sessions, but with the availability of data, we've got more and more sort of citizen scientists that want to get involved and do get involved with the data, and we have to keep that in mind as well. That especially in this day and age, we've seen over the last few years that it's also very easy to become an expert on a subject by just reading a couple of blog posts, and then it's fairly easy to undermine someone's research. So we have to keep that in mind, that we also have a duty to provide good software description, good data, that if someone wants to run something as a citizen scientist, that it's also easy for them to reach the conclusions that we have reached, and it make it more difficult to come to wrong conclusions. Right. I see there are some people writing stuff. So how do we achieve reproducibility? And it's sort of, it's going to come over there will be a couple of slides connected to it. But one of the things that come up in discussions is, again, connected to the previous slide, is what do you expect from reproducibility? Is, well, how much reproducibility do you need? How much reproducibility is enough reproducibility for you? And is 100% reproducibility even possible? So I've spoken to people that for them, it's enough to run the experiment and run a simulation and get a result, and get the result within a certain, with a certain sigma. You repeat the simulation, you will get some different results every time you run it. They understand it, but that's expected for them. For them, it's just a thing of writing a paper is to clearly communicate it. But on the other hand, I've spoken to people that they expect when they run the code that whenever they run the code, they get answer exactly the same every time, no matter what hardware they run it on. No matter, well, software stack. That's kind of an obvious thing that you might get differences there, but mainly no matter what hardware they run it on. I've spoken to a person that wanted their code to give exactly the same result, run on a CPU and on the GPU, and this is a very, very, and their requirement was especially pretty much down to a single bit to have exactly the same results, which if anyone has done any parallel computing will know that it's very difficult, if not impossible, to achieve. But there are people who see reproducibility like that they really want to have a 100%, the same results every time when they run their experiments, when they run the piece of software. So they can't compromise. So yeah, as Peter commented here, even between running on N processors on OpenMP, you will get different results. Yes, and that is a common thing in programming. When you're operating, on floating point numbers, A plus B plus C does not mean equal to B plus C plus A. That's that's just the nature of how these things operate, and the more parallel you become, the more obvious that becomes. I run into that trap multiple times myself when I just forgotten that I'm how can you forget that you're working on floating point numbers, but you just check whether some results equals to the given number, and even running a summation simple sum on NumPy, and running then the same sum, technically the same sum on a GPU, can give you a result slightly different to like 6 decimal place on a 6 decimal place. So for me, for example, that would be acceptable. For me, that's a reproducible result. But for some people, that's just unacceptable. And yes, I see a comment that expecting identical outcomes on different hardware architectures shows a lack of domain knowledge. Does this not? Yes, I would say so, but as I said, that's again just my opinion. And some people would disagree well, as I said, I've spoken to people that would disagree, that they just understand that they think, you know, it's just write it code more carefully. But yeah, I think that might just come to this sort of yes. I think that there might be a bit of an ego, or as you said, it's just a lack of fundamental understanding of what's going on. And surprisingly, it's that was mainly, you know, as again, as I said, your experience, your mileage may vary. That surprisingly didn't come from, you know, scientists turned software engineers, or you know, observational scientists turned software engineers. That very often, to my surprise, comes from people that either did some computer science related degrees, or have been in software engineering most of their career. Yes, I see someone, Thomas, raising the hand. I don't know, because I don't have a participant yet. Okay, yes, Thomas.
Yes, I'm on now. Yeah, I'm the guilty party who.
Matthias, you can, as co-host, you can promote anybody, especially the one who raise their hand, so you see them in the list of attendees.
I cannot see the list. I don't have access to participant list. It once I was made a co-host, it disappeared.
You co-host,
for some
and
reason.
then you can show the list of participants. So now we have.
Let me. Goodness, has that disappeared? No, I cannot see the list of participants.
Hi,
Unfortunately.
Can you see the list of participants? There are two panels, one for the panelists and one for the attendees.
So
no.
Thomas Jürgens has raised his hand.
No, I cannot see the list of participants. I was wondering about it.
Okay, I can be in charge of that, of giving
that would
people
be great. Thank you.
The rights to talk. Okay.
Thank you. Sorry about that. Yeah,
and Carla is going to promote Thomas as panelist.
Yes, you did. Thank you very much. I'm the guilty party who sent that comment on Discord about the lack of domain knowledge. Well,
I think it's a good comment.
Isn't it one part of our education, the scientific education, that we learn to, well, say, well, there my domain knowledge ends, and I don't understand really why it's not reproducible. Let's call in the cavalry, right? Let's call in the professionals. Hey, Matthias, you do GPU number crunching all day long. So why is my result not reproducible on your hardware? Why is it only reproducible on my tiny laptop, and your big ion can't reproduce this simple result? So why don't we ask that question? What's your take there?
Yeah, I don't know. I think that one thing I will talk about. I think, you know, you touched on that, upon, you know, how we are taught how to do it. A lot of us maybe come from backgrounds that we are, you know, observational astronomers turned you know, software engineers, and a lot of this stuff is you know, when I was, say, taught programming at university, there were very basic courses. You know, there was stuff taught along the lines of, oh, you know, you tell a computer what to do, it does it exactly how to do it, or phrases like, okay, you can express any number you want exactly, or any number you want as a binary representation. So maybe it comes a bit to that you know, the lack of understanding, and you know, I personally, if I knew that something was broken, or if I didn't understand, I knew that I would ask someone. Maybe it is the problem that people don't understand that there is a problem. I don't know if that's clear. Or maybe, you know, I'm just too hopeful and too naive that I would believe that, you know, whenever people don't understand something, and and see that there is something wrong, that they would ask a question, and they don't really do that. But at least I hope that partially it is the case that you know, it's still not well understood that there are problems, and
Yep.
and yeah.
But Mateusz, look, just a year ago, I worked for Astron, right, within the for the LOFA telescope, and well, we had to update our very simple basic pipeline, one of our pipelines from to C++11, right? And so I took the task and updated everything and made the code compile and just run fine and prepared the Docker images, and then we just fed some simple data to it, right? And then the data came out, and the result was that it was not bit identical. Yeah. Just by switching a compiler from C++98 to C++11, yes, right? Yes. And having to update the compiler, having to update the Linux distribution because the compiler wasn't available for the old distribution. So a very long story cut short. That was the moment when I thought, this is something I have no clue about. I better call in help, because boy, this is not something I would have expected, you know, yeah, because I'm naive, like you described, right? I didn't get fed the numerical recipes with a spoon. So to me, that was quite surprising. But well, yeah, that was the moment of enlightenment where I said, yeah, well, now it's time to ask my colleague Mattia Mancini, who actually took on and trying to explain that to me and others. And so we worked out then a process where we could actually compare the results. And they took a long time to explain that to me with standard deviations and all that, numerical noise and all these things. And that gave me a great understanding. So there's something to gain, right, by asking others.
Yeah, no, I personally, you know, I definitely agree. And when I see the problem, you know, as you said, we don't know it all, and then yeah, we definitely don't know it all, because it's all such a complex. Everything is so complex these days, but you know, I unfortunately I don't think, you know, as you said, you know, based on everything that you said and what are we talking about here, unfortunately there is no, I think, concrete answer to that, because that will just depend on the person, you know, as you said, you know, there will be factors of, you know, personal preference, personal sort of beliefs, and unfortunately ego. You know, all of us, no matter how much we say that we don't, we all have, you know, our own pride, and unfortunately sometimes that prevents us, you know, from either asking questions or thinking, oh, you know, I can do it on my own, I can figure it out on my own, you know, I've got a PhD, I've got a master's degree, or I've been writing software for 30 years or whatnot.
Yes,
you know, a lot of us think I can do it on my own, you know.
I absolutely agree. I'm in many of the categories that you just described, and pride is the number one on my list. Of course, I'm proud of what I'm able to do and all these things. But isn't that then that we're asking the wrong question, right? Shouldn't we be surprised that the results are reproducible? Shouldn't we expect then? Should then the basic expectation not be, okay, my results are not reproducible. Why are they?
Well, as I said, it's I think it's again back to you know, I think we are coming back to what we mean by reproducibility, because for everyone else that will be a different meaning, because as I said, for an engineer, a reproducible result might be something different to, you know, someone expecting, you know, an exactly bitwise reproducibility, which, you know, I asked this question, is 100% reproducibility even possible? And my opinion is, if we mean that by reproducibility, exactly 0 and 1, zeros and ones, exact sequence zeros and ones every time you run the experiment, then I think as what you said, yes, then we can't have reproducibility, and then the whole idea of reproducibility is thrown out of the window, because by the very definition, you really can't have reproducibility in this sense. Yes, as you said, you sat down with your colleague, you understood, that there are, equations that tell you, error rates and everything, depending, especially on floating point operations. Then it's the sort of, as much, then I would put it to as much as reproducibility as possible, with an explanation of why don't you have 100% reproducibility, and then I would still count that, as a reproducible result of, is not 100% the same streams of 0 and 1s, but clear explanation of why it's not exactly the same. So I think, then that would count as reproducibility, because I'm in the camp that does not, would not count as I said again, the bitwise hardware reproducibility, strict hardware reproducibility as a cornerstone and as a necessary thing for absolute reproducibility.
So that connects nicely to Kai's talk yesterday, right? If we know the uncertainties, if the uncertainties are certain, yes, which means we have the means and the knowledge to explain them, then reproducibility becomes a much better defined subject.
Yes, yeah. I mean, and it's not only. I think with uncertainty, it goes down to how many people understand science, even also scientists, that certain things are stated as facts, and with uncertainties either swept under the rug or pretty much not taken into account or not explained clearly. So I think yes, that should be an essential part, taking these into account and making sure that we communicate them better. Okay, I see we've got more people joining the discussion. Yes.
Hello.
Hi, can you hear me?
Yes, yeah.
So one important aspect, I think, is unit testing of software. So that's a relatively easy approach, I would say, with PyDat-test if you code in Python. And I've heard good suggestion to first write a unit test and then write the real function we were thinking about, and do it every time you basically write a function. Thank you.
Yeah. So this is one of the things. Well, I think that there is on later slides. So I think we can have a more detailed discussions about how we can actually achieve that. I think sort of maybe it's. I agree that unit tests are important. That testing is very important. I hold a slightly controversial view of unit tests. You say write unit test first and write a function. I'm of the view of the same people that write a function should not write a unit test for it. And I've been told of many times for it, but I stick with that. I've seen many examples that when that goes wrong, that the person that writes a unit test writes a function as well, and then stuff goes wrong. Yeah, I think Susanna wants to.
If you have human resources, then of course people.
Yeah. That goes back to human resources. Yeah, but I think, as I said, there are There will be place to talk about, I think, unit tests later in the detail, so we can come back to that. I know. Sorry, Susanna, can I give the floor to Samuel first, because he's been waiting for a while.
Can you hear me?
Can you hear me?
Yes, Samuel, I can hear you.
Yeah. Before I say my comments, just a quick comment on unit testing. You said you come back to it, but I think that for the subject of reproducibility, unit testing, where it's very strong, is just to give you confidence that your piece of code or solution works the way you intend for it to work, but not necessarily to reproduce the results that your solution brings.
Well,
to my comment on Discord, my frustration with reproducibility, of at least from my experience so far, has not been really with the results to say that is it exactly as what you get when you run your code, but it's been to even run the code and have it run the same way it ran on your environment. And that has been my frustration. So somebody has a piece of solution, a piece of code, they share it, whether from a colleague or from a paper or whatever, and you get that solution, you try and have it just run in your environment, and that never gets to run. So resolving that first, even that to have it reproducible in the same way on someone's machine as yours before you even compare the results, I find that also very frustrating. And things like containers come in useful for that.
So we will talk about it, like, the tools that we have for reproducibility. But one thing, for unit tests, you can see it as the way, I think we've already talked about it before. When you've got a unit test, you can run it on different machines, different hardwares, and when you get results, when you get results from your unit test, you can I can envision it, being useful to compare on other things, but I think one thing is we do underuse and underappreciate unit tests, definitely, and there is I think greater scope for using them in whether it's software engineering or just general science. Susanna, sorry to keep you waiting. I know you tried talking a few times.
Hello, can you hear me?
Hello. Yes, I can hear you loud and clear.
Thanks. I just wanted to make a comment related with reproducibility, and something important is that we need to take care of scientific reproducibility, which means that because it's a basic in the scientific method. So if a study is not reproducible, it's not a science, no. So we need to take care of that, and this means that. And this is something that gives us a definition of what reproducibility means. So we know from many years ago that scientific reproducibility means that an external group, a different person can get the same results of a scientific study, maybe using your same data, using your same method, but the scientific result achieved is the same. So maybe when you talk about to get exactly the same results, exactly the same values of after running a pipeline, we are talking about repeatability of the experiment. But maybe this not mean that the experiment is not reproducible if you don't get the same exactly values for your results. Because maybe this not change your scientific results. I mean, maybe that depends not only of the field, but the experiment itself. If you run your pipeline in a different platform and you get different results, but the scientific result, it doesn't change, your scientific experiment is still reproducible. So we need to take care how to achieve scientific reproducibility, which I think this is an important thing, because it's what differentiates what is science from what is not science. And for this, we need many things, the availability of the data, the software, the platform, the ecosystem, the configuration parameters, all these things that are around the FAIR principle that all we know. So I would like to say, yes, about reproducibility, that we need to differentiate with this. Something that is replicable, something is reusable, something is reproducible. So there are different meanings, there are different flavors of reproducibility, but I need to focus on scientific reproducibility.
Well, yeah. So this is, you know, maybe what I said indirectly, that you know, what I would like to see is people, you know, at the end of the day, focusing on maybe science and not, you know, yeah, just getting bogged down on these, you know, small differences in the results. But at the same time, you know, understanding, because, you know, to be able to say that, you know, your science is reproducible, God, this word, that, you know, your science is reproducible. You have to still understand, you know, what your software is doing, so that you can attribute, if there are any differences, you know, you first, you know, your first point usually is, if you get different results, if you follow, you know, exactly the same recipe for experiments, that, you know, every experiment that wants to be reproducible should provide, as you said, same data, same pipeline, same methodology. If you get different results, you know, you should, I think, understand where that difference comes from, and you know, in this case, you know, understanding what your software is doing, I think it's fairly crucial for understanding, you know, whether, you know, it's something wrong with the results, or there's something, you know, wrong with the software, and you know, you can only start thinking about, you know, science in this case, whether you broke the science, or there is something wrong with original approach or your approach, or maybe you've done something wrong in trying to reproduce the experiments, after you discard the sort of software the software component. But yeah, I agree that, you know, I think the scientific reproducibility is the sort of ultimate goal, and you know, that's what I'm trying to say here, that, you know, things like getting every, you know, as I said, as I keep on saying, exactly the same bitwise representation on every hardware, that should not really be of much of the concern, as long as it's not, you know, as long as you can live with, as long something as you can live with, but you should still understand, you know, how the software works. Right, I see there is a you know, lively discussion on Discord. If I miss some of the questions, I'm sorry, but there is a lot of going on, a lot of people writing, and I'm trying to keep up, I promise. So there is a lot of questions, a lot of the stuff about, you know, being able to run the source code and stuff like that. So we will talk about it in a second. So now you know, to point a finger at each and every one of us, you know, can reproducibility be optional? And I think the answer in the grand scheme is no, but just, you know, look deep down into your soul, and think about, you know, when was the last time, you know, you've done one of these things of, you know, only you will use this code, or you will write the documentation later. You just want the code to work, and you're just gonna employ this quick hack for your code to work. All of these things, you know, really diminish the, in my opinion at least, diminish the scope and reproducibility and reusability of your code. So we've already talked about it briefly, you know, what are the tools for reproducibility? So, you know, I think starting on, we were talking about, you know, okay, how and there is a lot of talk in the chat about different algorithms, and and you know, the sort of the bitwise representation. But what it comes all down to, as it was mentioned, that as we talked, you know, a couple of minutes ago, literally, that at the end of the day, you know, we should care about science, no matter what piece of code you write, or science that you enable with your piece of the code. So, you know, we need, you know, data, and we need algorithm of what to do with the data. And by the algorithm, I don't mean, you know, a computer algorithm, but the sort of methodology of what to do with the data. So no matter whether you're just designing the experiment or whether you're writing a software, you know, the really key starting point that I think is, I mean, I'm guilty of it myself, that is not given much thought, or is sort of, again, swept under the rug, is documentation. And as I said, well, it can be software documentation or methodology documentation. And then is the case of, you know, as I talked about, you know, from the point of view of software administrator, software manager, system administrator, and things that people already talked about in the Discord channel, that, you know, how can you care about software reproducibility or about science if you have to first spend, you know, 1 or 2 days of actually, you know, trying to compile your code or even make a code run if it's in a language that does not need compilation. And you know, we've got ways to help with that. You know, we've got things like containers, the containerization technologies. That's the one word that I said would be more difficult. Containerization. I always dread this word when I have to say it. You know, nowadays we've got consistent Python environments with Conda. You know, we can distribute notebooks, so we can kind of ensure, at least at the software level, you know, it's getting better. So you can kind of at least ensure, if you are careful, the sort of consistency of your environment. But on the highest level, and I think it might be one of the more difficult ones, is having a consistent and really consistent philosophy that is really set in stone, and you know, really put reproducibility at the center, really, of a lot of software development. And again, you know, what we talk about, you know, within your team, decide what reproducibility means for you. Have, you know, metrics for reproducibility. Have, you know, sustainable, what I would call metrics for reproducibility, not things like, you know, we talked about, you know, have a good understanding of reproducibility, and one thing that I will talk about later, and you know, maybe that was connected to the talk about the bubbles. Understand what different parts of your processing chain do, and how they understand reproducibility, and how they approach to reproducibility will affect your results and your reproducibility. Right. So there is a couple of things. You know, are there any sacrifices that we have to make in terms of reproducibility? So you know, as I already said, if you know, start an experiment, and usually on a tight budget, so maybe, you know, time is important for you because time is money. Maybe you don't have time to, you know, develop a coherent reproducibility strategy. Maybe you don't have time that, you know, it's being followed. In an ideal world, I could imagine, you know, every team, or at least department, having, you know, a person that is, you know, sort of high level reproducibility champion, or within the team, almost like a, you know, scrum master, having a reproducibility master. Do you have to, change your work environment slightly? Does it have to adapt? Do you have to maybe use slightly less convenient programming languages or paradigms? And what about legacy software that has not been written with reproducibility in mind? Can you afford to spend time to make it reproducible, to ensure that it is reproducible? Again, on the most basic level, even going back to the software, writing documentation, fixing documentation, making sure it runs on a bigger proportion of the machines. It's mainly, can we afford that, both in terms of money and human resources? I think there's one thing that we talked about, that very often our teams in best case scenarios are small, and the worst case scenarios are very, very small. And one thing we talked about, and there is a lot of chat going on, I think, about that, but it's something, again, yes, as was said, scientific reproducibility, that is really the ultimate goal. So I wouldn't like to get bogged down on that. But portability, there are a large number of available platforms. You can have, as we said, differences even within the same generation. And as I said, going between CPU and a GPU, you can have a difference, or even on the same CPU or GPU in the same architecture, you can have differences going between different GPUs. And I've, speaking to people, how they handle it. Some people say, okay, they just limit the number of available platforms. Those of you, hopefully most, that were using internet in the late 90s and early 2000 to mid 2000, it's sort of the equivalent of works the best in Internet Explorer in resolution 1024.768. That sort of approach that limit the number of available platforms. But then my question is, can we actually call it reproducible then? The idea is that, basic idea of reproducibility would be, you get the data, you provide the data, you provide this methodology of how to repeat the experiment, and you make sure that whoever wants to repeat it repeats it. And I think, then by limited the number of available platforms, that stands against the very, very core of what it really means for the science to be reproducible. Right, so now I understand that this is going to be a very controversial slide, and I'm expecting, Discord to become red hot, and just just ground open up behind me and swallow me when I answer this question. So I understand I might become an unpopular person now, but I will ask this question. So it's not meant to it's mainly meant to provoke a discussion about, again, how we approach the reproducibility, and very much connected to the slide of sacrifices in the name of reproducibility, and where we put reproducibility and sort of our development. So let me ask it. If we care about reproducibility so much, and when reproducibility in science is important, why do we use Python so much? And I can already imagine a lot of people asking, oh my God, what is this guy doing? But think about the last time you try running a piece of software, Python software, on a slightly different cluster, on a slightly different setup, and it didn't run, or it did run, and it gave you completely different results. And I understand, this is not, Python specific. I just put it as an example because for the last 8 months I've been working, primarily and pretty much only in Python, and that's been cropping up, pretty much every day. Famous example, print versus print is the least of your worries, when moving from Python 2.x to Python 3.x. but it's common with a lot of other languages. Pretty much anything that uses external library or external module that is maintained not by a we could imagine core team, core consortium, that will be a problem. So it could you could almost replace Python with non-standard C++ libraries. So if you ever used Boost in C++, you will have the same problem, really. But I think Python is much more common, and the main thing is whenever we have nowadays new PhD students, new master students, new undergraduate students, I think Python is the first language that we teach. Very often, for a lot of people, it's the first time they ever write a program. It's in Python. So that brings me to a question: is how, if at all, do we teach reproducibility? Because I remember, or don't remember, being taught, as I said, in any of the programming context about reproducibility. Maybe a bit in the lab, that in the physics lab, but never in the sense of software development. Yes, we've got someone.
Yay! Well,
Yeah.
I think this does touch on a point I was already making on Discord, right? I mean, it's sort of, how do we teach reproducibility, or how are we not taught reproducibility? Indeed, the answer from me would be, I've never been taught to be reproducible. Also, when I was when I still was a real astronomer, let's say, and it feels to me very much like I mean, I find reproducibility very important, and I mean, I'm very passionate about the topic, and I'm very happy I see so much discussion on the Discord on it being found important by people. But it feels very much like there is not really an incentive from anybody to be reproducible as a scientist, because I think I've never met a scientist who has ever, well, maybe I have ever met a scientist who has ever tried to reproduce anybody else's results. But I mean, it's not that people are so happy, like, hey, look how cool I am. You know what my career is about? It's reproducing other people's work.
I think you touched on a very important subject here, that for a lot of people, I think if people do it, they do it, maybe in their spare time, or to hope maybe, that they try to repeat some experiment in the hope that they won't be able to do it, and they will be able to publish a rebuttal paper. I think it mainly comes back to the point that, you don't see papers that, because a lot of it in science world and academia is about how much papers you can publish, and how much how much exposure you get from your research. That there is no, as Jose said, and you said, and what I wanted to say, that there is no incentive to run reproducible research, because a lot of the time, there are certain experiments that you can do within your spare time, you can reproduce them, but how, for example, you go around reproducing a result of a simulation that took months to run on a supercomputer. I don't see any funding body providing tens of thousands of pounds to run a supercomputer for 6 months just to prove that someone's result was correct again. And you can't publish, in this case, a paper saying, okay, we run it again, yes, our results agree with what this previous paper published, because papers like that were accepted in the 1900s or early or late 1800s, late 1900s and early 2000, 19th century, early 19th century, but not anymore. I think that this is the problem, that You don't really have scientists that say, okay, I just try to reproduce everyone's research in my spare time. It's a lot of the time it's mainly that, you know, when they see something controversial and mainly come already pretty much from the conclusion that they're going to prove that, you know, something went wrong and something is really wrong.
But Mateusz, isn't that then the task of the peer review, right? To a certain extent, of course, we need to cap that, because not every peer review can have that multi-million euro cluster at their disposal. So shouldn't the peer review guarantee that we can reproduce the scientific results presented in the article or in the paper? I mean, that is what the peer review is for, right? That we have a scientific sound article, that the results are reproducible, and that the other peers can rely on what is said in the paper, because that is the foundation of the citation system.
Yeah.
Right? I mean, if that is not happening, then yeah, what the hell? I mean, the whole thing doesn't work.
Yeah, I agree, but then again, it's you know, the peer review is done by you know, human beings, and again, as Jan said, you know, with limited amount of time and doing other things, you know, focusing on their own research. So, you know, how willing would someone be to, you know, how to ensure to you know, work on someone else's really research just to ensure that it's correct.
Yep, but what's then the point of the peer review? Sorry, what's the point? The gatekeeper to not let citizen scientists in? Come on.
Yeah, no, I really agree with you that it should be, you know, really. I would personally see this as a core thing of peer review, you know, making sure that results make sense. It's just, you know, we do have to, I think, recognize that in certain situations it can be difficult, you know. As I said, let's go back to this, you know, the 6 months running simulation. You know, what would be your, you know, expectation of peer review? Yes, the results make sense, but you would not expect them to run the simulation all over again, because they can't do it. So in this case, you know, then the definition of reproducible might change, because results scientifically make sense, they are sound, but you have to remove this sort of reproducibility from point of view of, you know, running the software and making sure that software, when you run again, that it provides the same result. So I think it's a very complex thing in this case, in terms of, you know, in terms of the peer review, and I think we could discuss it, you know, much more in
another
detail
BOF.
yeah, because, well, you know, you could pretty much have a whole separate BOF, to be honest. In this case, maybe for next year, you know, the role of peer review and in science, you know, and you know, and in reviewing not only scientific papers, but also, you know, what would be the role of peer review in reviewing software papers, that we see more and more journals are accepting them. You know, can we implement the same standards, or should we have extra standards, you know, for reviewing those, whether they, you know, make sense not only from algorithmic point of view, but, you know, can they do, what is their reproducibility potential? I see there's Vladimir wants to, has been hanging around for a while. Vladimir?
Oh, Thank you. I was just listening in. I just wanted to chime in with some points and maybe opinions.
Yeah, of course, of course.
But first, I want to comment you on the slides that I see right now on Zoom, because that does reflect many of my own convictions in the subject. I have various experience with making software reproducible to a certain degree. And in fact, I actually like to do it as part of the process. When I finish another iteration of my code, I actually try to run it, and then I want to see what changes. And the kind of things that I'm doing are complicated enough. It's a multi-threaded code that is optimized for speed and all that. Naively, I would have expected it to have different results every time I run, simply because when you add floating points in different numbers in different order, you're going to get things that end up varying with the last digits. And the things I always keep being surprised by is that by and large, that actually doesn't happen. But what I do see all the time is that even for like very simple C software, the places where it gets loaded, the amount of memory it uses, how quickly it runs, that all changes all the time. And so the question of making the software to be, say, bit by bit reproducible is a really tricky business. One experience that I have, that I know of, that not personally, but through another person who described it to me, is that they were developing a computer game for tablets. And the idea was it would be multi-user game where people would go and play. And because it's a networking game, they don't want to transmit all the states. They thought they had a bright idea to only transmit the player moves, which is when they very quickly figured out that you can transmit the player moves, and then players will actually end up in different places on each of their screens, because the software will actually aggregate those moves in a slightly different manner. And when they started trying to make it reproducible, it turned out it was not just a matter of coding practices or like test cases or not, but it's actually algorithms. There are some algorithms that work, some don't. Different CPUs on the same Intel computer, you might use EVX or you might use FPU. You'll actually get different results. If you have a big cluster, you would have a problem that we have these things called cosmic rays. They strike the bits, they flip them. You will actually end up with results that are flipped. You will end up with bit rot in your code and your data. On a big cluster, I often have a situation where if I simply to run the software and blindly trust the result, I would actually have a certain fraction of corrupted data back. I have hash some checks that are being computed while the software is running to actually let me know what's going on. And so from this point of view, it's not just the issue of other people trusting it, but of you actually keeping control of what your code is doing. So it is important. But on the other hand, I also view it from a statistical viewpoint. So if I produce results that I'm saying, say, 95% confidence level, then if I have 0.1% of stuff being non-reproducible, it's really within the tolerance that I have. And so that's fine. And perhaps the best way to reproduce results would be to observe them with something else. If you have a radio telescope result being confirmed with an optical telescope, this is like the ultimate reproducibility because everything is different. So I think this is, it's important to focus on your software being correct and reproducible in this way. But we also shouldn't lose focus of the fact that underneath all of that is physics, right? Physics, astronomy, actual real stuff. And that is actual reproducibility. And there is all kinds of really interesting things happen that really have to do with physics.
So that's a great point. Thank you. I don't know who is next. Susanna, I think.
Hi, thanks.
Welcome back.
I would like to come back to the peer review, the review process a moment, because something that I think we need to think about is that we need to produce we need to develop tools to support this process. So we are not in an era in which the data sets are huge. We need to access to distributed computing infrastructure to run the software, to access the data. And we need to be able that the reviewers of our scientific experiment can access to all these environment in order to verify our results. And this is very important, and is related what I mentioned before, that the availability of the method is not just that they are publishing somewhere, but that is easy to use the data, to run the software, etc. And this is something that we need to pay attention now, that this software is not running anymore in your laptop or in your computer, but in remote computing centers that you need to a login and a password to run the software. You don't know where is the data. All these things that even for the people working in the collaboration is difficult. Even more difficult is for the reviewer. And this difficult a lot the reviewing process. So we need to focus also, I think we need to pay attention on that. So
I do agree with you, absolutely. And I think, you know, as I said at the very beginning, I think we see that in many you know, BOF sessions, that is that are here, that, you know, we do take it seriously. You know, that you know, how it's like 2-3 BOF sessions about, you know, standardizing data formats, archiving, and things like that. So yeah, I think that's the key. You know, we did spend a lot of time, you know, talking on this sort of what I would call a low level reproducibility. But the starting point, as I said, is this sort of high level, you know, when I said, you know, you would almost put it under the documentation / methodology, that, you know, you make data accessible and you make software accessible. Just, you know, that's the first really point where you really start thinking about reproducibility, you know, making data and software available and easy to run. And that's, you know, what I think, you know, things like, you know, containers, you know, the things that I listed a couple of slides ago, containers, notebooks, come into play. But yeah, as you said, you know, and stuff that is very often neglected, access to the data, because, you know, that also costs money, but that question is asked, you know, very often. You know, how can I get the data? Oh, it's behind this VPN, behind this SSH, and you have to go through these many login nodes to get the data, and it's not accessible anywhere easily, as you said. Sometimes, you know, people within the team have problems with either accessing the data or running the software. So how can we expect someone outside the team to be able to rerun experiment and get some useful insight if we, you know, within our team, we cannot guarantee that? And I think that goes back to what I said at the, you know, again, a few slides ago, to, you know, the philosophy, really, the changing approach of, we not, you know, maybe to use the nomenclature from yesterday's BOF, that we are not in our own bubble, not only, you know, bubble of software engineering or scientists. Within a group, we're not in our own bubble. We have to make sure that other people can use our research and can reproduce it, and, you know, can question it, because, as you said, this is a cornerstone of science. So I think, you know, we should start really, you know, before we go on to looking how, you know, floating point numbers are treated on CPUs and stuff. This is you know, what I tried to, you know, say at the beginning. This didn't really be. We did spend a lot of time talking about it, and I think agreeing in a lot of cases that, you know, that's not the exact focus on reproducibility. It's what you say, that should be really the end goal, and everything else is really the means to achieving it.
other comment related with that is that maybe we need to think about in which kind of metrics we think that could be useful to incentive reproducibility. Because we know it's true, there is not incentive at all, as Pepe Salter said in the chat a long ago. But I think the tendency is changing. Now in the Europe, there is some rules in order to incentive this kind of the openness of the data and the methods. So we all know that the tendency is changing. But now that this is changing, we need to think that, okay, what is the best metric to evaluate how reproducible is a scientific method, a scientific experiment? Because all can we agree that the availability of the data and software is the first step, but maybe this is not enough.
Yeah, no, I think, you know, it's not enough. In my opinion, it's definitely not enough. But it's an important first step that, you know, we should all take, because unfortunately it's an important first step, but it's still lacking. You know, it's a first step that many research groups and institutes have not taken. And as you've said, I think if not by asking, is by forcing research groups to do it, because a lot of, you know, I see more and more funding bodies, they add, you know, the data accessibility or even software accessibility they are adding as a requirement for, you know, funding reviews and things like that. Of course, there is still a question of, you know, you've got a proprietary data, your data is protected for X months before you have to publicly release it. But I think, you know, one way is really, you know, and that's really on funding bodies in this case, ensuring, you know, enforcing the fact that the data is and software and the methodologies are released, and you know, not only brief mention in you know, at the end of web version of your science publication, but somewhere, you know, that is easily accessible and pretty much, you know, step by step, reproducible, you know, almost example. Yeah, but I do agree. I do agree with the things that you said. I think, yeah, we've got someone else waiting to speak. So thank you, Susanna. I think we can talk about it later. We've got someone else waiting. So sorry to keep you waiting. Hello. I've heard something for a moment.
It's Enrique. I can try to ask him to unmute.
Yeah.
Can you hear me?
Oh, I can do that as well.
Yeah. Hello, Enrique. Yeah.
Hi, somehow I was unmuted all the time. Okay, so I just wanted to mention something very similar to what Susanna said. No,
We hear you, Enrique. There is some background for me in the background, so my neighbor is drilling holes, but we hear you. Please speak. Yeah.
Okay, so going on the lines of peer review and how reviewers can reproduce the results. No, I think we should enable tools that allow to somehow ease the task of reproducing results, right? So imagine that, I know, something like you have results in your paper, let's say a graph, for instance, and attached to each of these results, there is a unique identifier that will give you some workflow, some way to basically reproduce the data, so that basically the task of reproducing will be as much automatized as possible. Of course, this leaves many questions also, no? As Susanna said, the fact that you can see how this was done doesn't mean that you have the resources, computer resources, or things like that. No, so there are many questions still to ask. No, I think the automation of reproducibility will be a good step forward to allow that.
Yeah.
And on a different topic,
definitely.
Yeah, on a different topic, containers are mentioned here. The containers are used in two different links of the chain. They're used by the final users, and for that, I think might be a good way to say, okay, I know that this is the container that was used to certify that something was working in some way, so I want to use that to reproduce the result. But if it's abuse in the other extreme of the link, basically by the developers who say, okay, this is the container in which we have tested everything, I think that can be dangerous. I think this has been also posted in the chat, in the sense that if I'm not able to reproduce my results in anywhere else, and I just say, okay, this is the container in which I certify my results, that is suspicious. I mean,
yes, well,
if you're vertical, if you are only able to reproduce the results in a vertical stack and not with some variations of it, that's fishy, I would say. So
yes.
this is a little bit dangerous to say, to rely fully on a container which maybe you keep unupdated for 10 years, and you say, oh, this is the only way actually you have to reproduce the results. If you are not having more moving parts basically under the hood and verifying that these moving parts don't change your results, then you can have little confidence that actually you are making a mistake, and just by chance basically with your vertical stack you are able to see the results, the proper results.
Yeah, I think, you know, I think it's going to be on my last slide. It goes back to the thing of, you know, understanding, maybe not domain specific knowledge, having domain specific knowledge, but understanding the tools that you're using and understanding the limits and understanding still what you can trust. Yeah, one thing is, yeah, containers have been, you know, on the market really for X years, very popular for the past X divided by 2 years. And a lot of the stuff that they enable is A, misunderstood, and B, as you said, is definitely abused. There are these problems of like, oh, if you want to reproduce my results, just run my container, and that should just give you all the stuff that you need. That yes, as you said, on one hand it is, you know, convenient. It is, you know, that's what I said, you know, from a sort of software manager or system administrator point of view, they enable reproducibility in the sense that you are able to provide a consistent, you know, working environment to someone. But yes, there is definitely scope for abuse, and one has to be careful, especially, yeah, as you said, when there are, you know, stale Dockers, stale images that, you know, worked once 10 years ago. Well, Docker won't have Docker working 10 years ago, so it was introduced in 2013. But yeah, Docker that worked in 2013, and since then everything changed. You know, the Docker engine changed, and since then, you know, even with the same stack, you cannot reproduce it. So yeah, there is a, you know, healthy dose of skepticism that we should I think apply to everything. So that's a very good point. Right, we're gonna yeah, we've got 2 people still waiting. So I think it will be our last 2 sort of vocal contributions, because we sort of very short on time. We're pretty much out of time. So let's see, Peter.
Yes, thank you. Can you hear me?
Yes, I can hear you very well. Yeah.
So great. I was really surprised. Thank you for organizing this. I mean, it's a topic dear to my heart, but what I hadn't realized is that your BOF is really the summary of why we are at ADASS. We all strive to write software that does the right scientific thing. You know, we hide it in the BOF and called reproducibility, but, you know, and there's many ways how we could deviate from the path, and that's why we're here. We want to stay straight on the path. So I really like this BOF in that sense, that this really summarizes why we're at ADASS.
So what you're saying is, if someone was meant to attend just one talk in the ADASS, is this talk?
Well,
No,
I think
I'm joking. I'm joking.
most
I'm
of us
joking.
have
Yeah.
seen all these ways how we can deviate from the path, and
Yes.
there's a lot of comments in the BOF that talk about that, and I really enjoyed that.
Yeah, no, I mean, this is, what I said at the beginning, a lot of these talks and a lot of other BOF sessions, they do talk about, things how we can achieve reproducibility, as you said, without attaching the word reproducibility to it. So, yeah, as I think I mentioned at the beginning, sort of like an umbrella talk, as
Yeah.
the
I'm just stating
practical.
the obvious.
Yeah, it's like practical provenance and it came up many times over the last hour and a half, how to, even simple things of how to provide the data to someone as a good first step to reproducibility. So I'm glad that you enjoyed this, and yeah, that was sort of my sort of plan to provide sort of like an umbrella sort of term and an umbrella maybe topic to combine many things. I see Dirk waiting here patiently. So that would be, I'm afraid that the last contribution, because as I said, I don't want to keep everyone waiting for meeting their breakfast and or / their lunch / dinner. So please, hello.
Yeah, can you hear me?
Yes, I can hear you.
I just wanted to echo part of the discussion in the Discord. The requiring a bitwise reproducibility is, I think, really difficult, even for the own group. If you think of algorithms that have sort of random initial conditions,
yeah,
Monte Carlo things and so on.
Yeah, I've seen someone mention that the Monte Carlo solution, by a pure definition, it's, well.
Yeah, so there has to be some margin, but I think the important part is that one describes the method to arrive at a result in enough detail that you can reproduce it yourself with the same or different algorithm, and more importantly, other groups have enough information from your publication that they can try to do the same thing, the same algorithm, but with a different implementation. And obviously this will lead to a result that is not bitwise comparable, but it should get to the same overall result.
Yeah.
It's probably difficult to describe what does it mean to have the same results. So what is the margin really? But I think this is the basis of science, that others can reproduce or maybe not your result.
Yeah. So I don't know how many participants are there in this BOF, and I was able to hear only few of you and see only few of you contributing in the channel in the Discord. But I think the general conclusion is sort of the same. I showed this this sort of the bitwise reproducibility as an extreme example, and I said at the pretty much beginning that, in my opinion, this is not what really counts as a reproducibility. But as I said, I wanted to provide it as an example that, some people that I've spoken to, they see reproducibility like that. And I'm glad that, a lot of us, the conclusion is that this is not really how reproducibility should be approached. This should not be at the core of reproducibility. But I think it's still for us to communicate it better, and I think the problem is that there isn't a clear definition of what a reproducibility might mean for us and for other groups. But I'm glad that we from the people at least that had a chance to talk to or read on Discord, that we kind of come to the agreement that this is not something to expect from reproducibility. Okay, thank you very much. So now the last slide, we talked about this state where we are, and where are we going? Where are we going now? Currently, I think we're in the state that I think was mentioned that currently still in terms of funding is, reproducibility is welcome by scientific community, but in terms of when you look at funding, it is optional. So I think one of the things is, is kind of tying reproducibility to funding as a requirement. We've seen sharing our code widely through consistent software deployments, notebooks, containers, but as I was mentioned as well, there is a scope for, trusting these way too much and abusing them. But, we are getting processing and pipelines are getting more and more complex, and it's hard to keep track of relevant changes in all levels. And a lot of stuff is currently, to be a modern scientist, the traditional astronomer, you still, have to understand, how code works and stuff like that. Where should we go? This is a concept that I've borrowed from web developer. I call it full stack of reproducibility. And again, maybe it's not for everyone to be as full stack reproducibility, I don't know, full stack reproducible scientist, to sort of have like a, reproducibility champion, if not in a group, but in the department person, that knows, how different steps approach and influence reproducibility. But even you as a scientist, I don't expect you to know exactly how, a piece of software works, or how, cosmic rays, bump your bits in the memory and how that influence bits in memory. Exactly, but sort of be aware of maybe back to yesterday's both, be aware of other bubbles and what other bubbles are doing. And, back to Python or C++, compilers and libraries. Can we as a scientist have influence on language developers on how the libraries are developed? We've had great talks with AstroPy that, we as scientists, contribute to that and have real influence on that. But can we as, large group of scientists, can we actually have influence on other libraries that are not purely science-based, like as I've mentioned, Boost libraries or C++ standard libraries? And mentioned many times, which I'm very happy, can we, create some set of reproducibility benchmarks or test suits for our reproducibility?
Fox, please wrap up, because I got to do a bunch of stuff for the next webinar.
And that's all. And I've wrapped up. Thank you very much. No, that's all I had to say. So I think, it was very useful. I mean, a lot of different incomes, and I think, I think the conclusion is that the reproducibility is dear to all of us, and we all care about reproducibility. I think now it's just the time. It's a great time. We've got the tools, really, with sharing the data, sharing our software, sharing our methodologies. It's starting to really, I think it's now the time. We've got the tools. It's time to start implementing it on the large scale. Thank you very much. That whale should not have been there. It just happens when you reuse slides. So thank you very much, and I hope the fruitful discussion continues on Discord. If you want to reach me, feel free to reach me on Discord or through email. I'm always happy to chat about reproducibility. If you want to work together, I'm really happy to get involved in some initiatives that people might have in mind. Thank you.
Okay, thank you very much. So this concludes the morning session. And big applause to all again. And so I will pass it on to Francesco, who has a number of remarks for the morning.
So yes, well, thank you again, Pascal and Anna Carla and all the speakers. That was an amazing session that we had today. I have one announcement. There is a cancellation this evening. I will repeat this. Okay, I will start my video. I will also, you can also see my
t-shirt. So there is a cancellation this evening. The talk about serving power users and novices, architecture and lessons learned with science platform MuseWise has been cancelled. The speaker is not feeling very well, and we hope he will recover soon. So we will. It's a 15-minute talk, and you can see it in the schedule. It's marked as cancelled. So we can use the time for more discussions in the two talks before it. Mark's talk on TopCat and Stefano's talk on microservices. Or just enjoy the break, I mean, and or. So that's the announcement. As far as the schedule, this is the only change that we have so far. We will resume today. We will resume at 11 a.m. UTC. That makes a little bit over an hour break. So you can, you can stretch, grab something to eat or whatever. I will be posting the new links for the Zoom webinar and the YouTube on the various channels, talks, posters, tutorials and stuff. 30 minutes in advance. I have to, start the new webinar and all that kind of stuff. Check out something super cool that Mark Taylor and Jose Enrique did. If you go into the website under program, there is streams, and these people are just sitting there watching the stream saying, okay, this talk starts at this time, this other talk starts at this other time. Fantastic, really awesome for yesterday and Sunday's talks. They're all indexed. So with this, folks, see you in an hour or so. Thank you again to all the speakers and the chair, Pascal, and Anna Carla. Thank you so much.